The leak NASA doesn't want you to see: the impossible motion of comet 3I-ATLAS on November 3, 2025. A quiet data pull from NASA's JPL Horizon system revealed something that should not exist. Hidden deep within the file structure was a single value, a line of code that defies physics itself: A30. That means perfect in-plane acceleration, with no motion out of plane. Natural comets simply don't behave this way. They tumble, they vent gas asymmetrically, and their paths wobble chaotically through three-dimensional space. But 3I-ATLAS isn't behaving like a comet. It's moving as if locked on invisible rails, gliding through the void with eerie precision. Its brightness remains constant between 14.7 and 14.9 magnitude. No flickering, no fading, no jets, no signs of volatile release. Yet, it continues to accelerate at a steady DV of roughly 60 ms, sustained over 20 days. And here's the part that chills every researcher who's seen the data. No one is talking about it. Not NASA's public channels, not the Navi Loeb team, just a handful of coefficients sitting quietly in a database, waiting for someone to notice. That same day, something else surfaced, a post on Foreign's paranormal board. The user claimed to be a PhD researcher with the European Space Agency, part of an ongoing project to analyze 3I-ATLAS observational data. The post read like a confession. For months, I have been part of a formal working group trying, and failing, to reconcile this object's behavior with any known class of natural celestial body. Whatever 3I-ATLAS is, it's not following the rules of the solar system. The official stance remains unchanged. ATLAS is a uniquely active, yet otherwise natural comet. But as new data emerges, that explanation is becoming scientifically untenable. Of course, 4chan is not a peer-reviewed journal. It's an anonymous image board, a place where anyone can claim anything. And yet this time feels different. The technical specifics in the mysterious post perfectly align with verified public datasets, the mass estimates, the spectral signatures, the observational anomalies. All of it matches. Most unsettling of all, the author's predictions are falsifiable. They offer testable timelines, precise behavioral forecasts for the coming months. In science, the messenger doesn't matter. The data does. So let's walk through what this anonymous ESA researcher actually claimed, because if even half of it proves accurate, we're staring at a phenomenon that should not exist under any known law of physics. It begins with the outgassing paradox. According to multiple independent telescopes, including the James Webb Space Telescope, 3I-ATLAS is ejecting roughly 150 kilograms of gas and dust per second. That number is not disputed. The mystery is what's not happening. Despite the violent loss of mass, the object doesn't move, doesn't recoil, and shows no rotational drift. As the anonymous post put it, it's like watching a howitzer fire a shell, with absolutely zero recoil, no smoke, no bang. A continuous violent event with no physical consequence. In the known universe, momentum conservation is not optional. Every action must have an equal and opposite reaction. But 3I-ATLAS seems to ignore that law entirely. A direct and disgusting violation, as the researcher phrased it, of the very foundations of Newtonian mechanics. Whatever this object is, it's rewriting more than a few lines of astrophysics. The physics that shouldn't exist. 3I-ATLAS and the impossible momentum problem. In space, momentum is law. If you throw mass in one direction, you must move in the opposite direction. Rockets obey it. Comets obey it. Every known object that ejects matter obeys it, except 3I-ATLAS. The anonymous researcher claims to have checked the data 100 times using every instrument available. The outgassing is real, the lack of recoil is real, and the numbers are beyond reconciliation with known physics. There's only one way the math balances. 3I-ATLAS must possess the mass of a small moon, compressed into a body no more than 2-3 kilometers wide. The lower bound estimate? 33 billion tons. Packed into a sphere barely the size of a small city. That density creates what the post calls a second. Worst problem. Finding a mountain-sized object on an interstellar trajectory is supposed to be statistically impossible. Until recently, our telescopes had detected only 2 confirmed interstellar visitors in all of recorded history. Oumuamua, 1I in 2017, barely 100 meters across. Borisov, 2I in 2019, roughly 400 meters. And then, Almost immediately after the Vera Rubin Observatory came online, we discovered 3IATLAS, a behemoth at least 5 kilometers across, 1,000 times more massive than Borisov, 1,000,000 times heavier than Oumuamua. If such colossal interstellar bodies are common enough that we found one within months of activating a new survey telescope, then our models of the galaxy are catastrophically wrong. The researcher puts it plainly. If this detection is representative, the galaxy isn't sprinkled with debris, it's swarming with it. That would mean our entire understanding of planetary formation and ejection physics is off by a factor of 10,000. Or, and this is the quiet, chilling conclusion that the research group is reportedly discouraged from discussing, 3IATLAS might not be debris at all. Then comes the chemistry, perhaps the strangest detail of all. Spectral data show pure atomic nickel venting from the surface, and it's happening at temperatures where nickel should be frozen solid. This isn't gradual sublimation, like ice gently turning to vapor. It's impossible metallurgy in open space, a process that defies both thermodynamics and common sense. The nickel switch, evidence of an impossible chemistry. What happens next breaks every rule of astrochemistry. The nickel emission from 3IATLAS isn't constant. It switches. A tiny fluctuation in sunlight and the nickel production stops instantly. A fraction more heat and it turns back on. This isn't random thermal behavior. It's binary. It's mechanical. And in chemistry, that only happens one way, through the breakdown of a parent compound. According to the Post, there's only one candidate, nickel tetracarbonyl, NiCO4, a compound we make on Earth. A compound used in industrial nickel refining. A compound that explains everything, especially the mystery of the missing iron. But here's the problem. Nickel tetracarbonyl doesn't occur in nature. Its formula is simple. A nickel atom bonded to 4 carbon monoxide groups. But to create it, you need controlled laboratory conditions. On Earth, we synthesize it through the MON process, pass carbon monoxide gas over impure nickel at 50-60 degrees Celsius. The nickel reacts, forming nickel tetracarbonyl, a volatile vapor. Then heat that vapor to around 200 degrees, and it breaks back down into pure nickel and carbon monoxide gas. It's an industrial purification method, used in electroplating, catalyst production, and high-grade metal fabrication. It's synthetic, unstable, and highly temperature sensitive. Exactly the on-off behavior we're observing in 3IATLAS. So what exactly is a man-made industrial chemical doing on a body that has supposedly drifted through interstellar space for billions of years? The researchers' words capture the moment of disbelief. What the hell is a synthetic refinery compound doing on a comet? And then it gets worse. The dust 3IATLAS is shedding, the fine particles glowing in its faint coma, is just as wrong. When you analyze how light polarizes off those grains, you can infer their surface texture and structure. And what the instruments are reading is unnatural, the dust that shouldn't exist, and the tail that points the wrong way. Every comet and asteroid humanity has ever studied falls neatly within a known optical and physical range. Brightness curves, polarization ratios, grain composition, all predictable. But 3IATLAS doesn't fit any of them. The readings came back so far outside the expected spectrum that the research director at first refused to believe them, insisting for nearly a week that the team had made a calibration error. Then they repeated the measurements and got the same impossible result. The data imply the dust grains from 3IATLAS aren't sand, aren't ice, aren't even mineral composites. They appear to be large, intricately structured particles, black, porous, and smoky, as if engineered from carbon fiber or soot, not natural dust at all, but manufactured material. And that's when things get truly strange. Both the Hubble Space Telescope and the James Webb Space Telescope detected a visual feature that should not exist. A faint, greasy smear of light pointing directly toward the sun, an anti-tail. Now, anti-tails do appear in some comets, but those are optical illusions, the result of perspective. When we happen to view a dust trail edge on, making it seem to point sunward when it doesn't. But not this time. Spectroscopic and geometric analysis confirmed that 3IATLAS's anti-tail is real, a jet of actual material being ejected toward the sun. The only way to explain it is a massive carbon dioxide eruption, venting from the sunlit hemisphere, powerful enough to launch dense, Heavy grains of water ice against solar radiation pressure. A directional engine roaring in defiance of physics. That would be strange enough, but there's a catch. 3IATLAS isn't rotating. Multiple observatories, ground and orbital, watched it for days without interruption. No spin, no tumble, no precession, nothing. Just a fixed, steady orientation. And a violent jet of matter blasting straight into sunlight from an object that shouldn't even have a preferred direction. The comet that refuses to change across every telescope, every light curve. The numbers are the same. 3IATLAS's brightness does not flicker, not by a fraction of a percent. The light curve is a dead flat line. If the object were rotating, as every comet must, and if a jet that powerful were erupting from its surface, we would see a rhythm, a pulse, a flicker. As the jet swept in and out of view, the brightness would rise and fall in perfect periodic waves. Instead, we see absolute stillness. That creates a paradox. The physics needed to explain the anti-tail demands a violent, one-sided eruption. But the optical data demand a perfectly uniform, symmetrical cloud. Both cannot be true. One of them is a lie. Either our model for the tail is wrong, or the cloud itself is not natural. Then comes the heat problem. Atlas is cold. Colder than it has any right to be. At its closest approach to the Sun, October 29th at 136 astronomical units, it was absorbing a torrent of solar energy. At that distance, sunlight delivers roughly 770 watts per square meter. For an object roughly 5 kilometers across, that's a thermal load in the trillions of watts, enough to power a small city. That energy has to go somewhere. It should be boiling away water in violent, glittering plumes. But the water isn't there. Spectroscopic data show that only 4% of the outgassed material is H2O. The rest is a cocktail of carbon dioxide, nickel, cyanide, and carbonyl sulfide. As one researcher put it, it's like pointing a blowtorch at an ice cube and watching it refuse to melt. Somehow, 3IATLAS is absorbing trillions of watts of raw solar radiation and maintaining an unnaturally stable low temperature. It has found a way to discard or regulate heat with precision, as if designed to keep its surface locked at a specific value. No matter how much energy it takes in, the path from nowhere and the shape of the room, the trajectory of 3IATLAS is, in the words of one orbital dynamicist, a statistical joke. It travels along a perfect low angular momentum orbit, the kind that guarantees a close pass through the inner solar system. There is no known natural mechanism that can filter massive interstellar objects onto such a precise path. When debris escapes from a dying star system, it comes in chaotically, with random speeds, inclinations, and orientations. But 3IATLAS didn't. It arrived almost perfectly aligned with the ecliptic plane, the flat, invisible disk where the planets orbit. Retrograde? Yes, moving against the flow of the solar system, but aligned within 5 degrees of that plane. The odds of that happening by chance? 0.2%, and the timing is even stranger. Its arrival placed it within tens of millions of kilometers of Mars, Venus, and Jupiter, while its closest approach to the Sun occurred directly behind it as seen from Earth, making it unobservable during its most critical moment. The probability of that alignment? 0.005%. Statistically, it's as if someone delivered it. For all intents and purposes, the Post concludes, this object was delivered from the darkness. And the anomalies aren't isolated. They're symptoms of one underlying sickness. A jet powerful enough to form the anti-tail should cause flickering. It doesn't. A body that massive should be inert. It isn't. The sun's heat should be tearing it apart. It feels nothing. Each contradiction is a wall, and together those walls form a room. A room we're standing in, too afraid to recognize its shape. So what is the shape of the room? What single impossible explanation could make all of this coherent? The anonymous researcher proposes one. It's a macroscopic quantum object, they write. A stable, massive particle, a remnant from the first microseconds after the Big Bang. A bubble of alien physics, wrapped in a thin skin of our own reality. In theoretical physics, there's a name for such a thing. A non-topological soliton, a structure that shouldn't exist in this universe, and yet impossibly does, gliding silently through the solar system, obeying a different set of physical laws. The cue ball hypothesis. when physics turns against its creator. Before you dismiss this as science fiction, you need to understand what a cue ball really is. This is not the invention of a novelist or a conspiracy forum. It is a predicted consequence of certain supersymmetric field theories, a legitimate possibility within the mathematics of modern physics. In the first fractions of a second after the Big Bang, the universe was a churning sea of energy fields, many of which cannot exist in the low-energy conditions we live in today. As the cosmos expanded and cooled, most of these unstable states collapsed, their energy decaying into the familiar particles that form atoms, stars, and life. But in some models, not everything decayed. Some configurations froze, forming stable, isolated pockets of energy, lumps of field that could not unravel, because they were protected by deep conservation laws in quantum mechanics. These are the cue balls, dense beyond comprehension, stable beyond any known material, and nearly immortal. They would drift silently through the galaxy, invisible, undetectable, interacting with normal matter only through gravity, making them a prime dark matter candidate. If such an object truly exists, it could have been wandering the Milky Way for billions of years, a ghost of the Big Bang itself, until one day, by pure cosmic coincidence, it passed close enough to a star for its outer layers to begin interacting with the stellar environment. This isn't a new fantasy, the Post argues. It is the only known physics that makes all the data make sense. And once you view 3IATLAS through this lens, the chaos resolves into a pattern that is both logical and terrifying. The object is no comet, no asteroid. It is a cue ball. 33 billion tons of exotic matter compressed into a compact core. Its engine is its own slow field decay, not destruction, but a gradual conversion of alien energy into ordinary particles, a silent transformation that has been happening since the dawn of time. The revelation, when the paradox becomes the proof, the so-called lack of recoil is no longer a paradox. It is the defining signature. What we once thought was a jet, a violent, directional burst, is something far stranger, an isotropic ablation, a perfectly spherical outflow of matter. The object is boiling itself from the inside out, yet the thrust cancels perfectly, because every reaction is balanced by its mirror. It moves without consequence, its fury contained in perfect symmetry, the toxic chemistry, the manufactured dust, the uniform cold that defies the sun. All of it suddenly makes sense. This is no comet shedding ice. This is an ancient reactor, a slow-burn furnace whose physics predates stars. The dust is not debris. It is slag, the ash of a process that has been running since the dawn of time. It does not regulate its temperature. It does not need to. The cue ball is indifferent to heat itself. The sun's gigawatts are trivial background noise to a 3 billion-year-old object with its own internal power source. It sheds sunlight as passively as a rock, because the sun is irrelevant to its existence. And the impossible trajectory, no longer a statistical miracle. It is not debris at all. It is one of them. A member of a hidden population. The unseen scaffolding of the universe. Dark matter, not as an abstraction, but as a physical presence, drifting through our solar system. We found one this easily, not because it is rare, but because they are everywhere. They are the quiet background of reality itself. For decades, we searched for dark matter in gravitational lensing surveys, in underground particle detectors, in collider debris. But what if it was here all along, passing through us, through Earth, through the solar system, and we simply didn't recognize it? The Post ends with two predictions, two tests that, if true, would confirm that the impossible has already happened. The falsifiable predictions, and the data that shouldn't exist. Science lives and dies by its predictions. If the theory cannot be tested, it isn't science. If it can and fails, it dies. But if it holds, we may need to rewrite physics itself. The Post offered two falsifiable, testable predictions. First, keep watching 3IATLAS. For a comet, activity follows distance. The farther from the sun, the fainter it becomes. As 3IATLAS drifts back into the dark, its carbon dioxide engine should sputter and die. But the Post claims it will not. Its light curve will refuse to fade. Its mass loss rate will remain impossibly high. Its engine, they say, is internal, constant, self-sustaining. If this holds true, 3IATLAS will violate thermodynamics for a passive cooling body. It will remain bright long after it should be silent, a dead ember glowing in the cold, driven by a heat that does not come from any sun. Second, listen for the engine. Its decay, if real, is not quiet. A cue ball's slow conversion of field energy is a 73-megawatt particle physics event, a miniature collider humming in the dark. That process must produce a stable, non-thermal high-energy signature. Point a gamma-ray telescope at it. If you see a signal that cannot be explained by solar-wind interaction or cosmic rays, then you are not watching a comet. You are listening to the heartbeat of an object that does not follow the rules. Then comes the date. November 3rd, 2025. That post appeared anonymously and on 4chan. That same day, official JPL Horizons data updated. The solution showed A3IATLAS 0 non-gravitational acceleration, perfect discipline, perfect control, no wobble, no spin, no deviation from the orbital plane, 2 independent sources, 1 anonymous, 1 institutional, reporting the same impossible thing. And here's what you need to understand. The Horizon system is NASA's definitive ephemeris engine. It ingests data from telescopes worldwide, fits orbital models, and solves for every gravitational and non-gravitational force acting on a given object. When Horizon shows a non-gravitational parameter, it's not a guess. It's the statistical fingerprint of a real force, a jet, a plume, a torque, a push. When it shows 0, it means the object is obeying only gravity, and doing so with mathematical perfection. That shouldn't be possible for any comet, but 3IATLAS isn't any comet. It may not be a comet at all. The equation that should not hold those parameters, A1, A2, and A3, aren't theoretical decorations. They are the coefficients required to make orbital models match reality. When the Horizon solution reports A1, was 162 at a sex 106 AU on day 2, AU 7.89 x 107 AU day 2 A3 0. It means something extraordinary. The data demand a continuous thrust within the orbital plane, radial and transverse, but none whatsoever perpendicular to it. 0. Flat line. Absolute symmetry. For comparison, take Comet Halley, the benchmark of natural cometary dynamics. As Halley approaches the Sun, sublimation erupts from its icy surface. Jets of vapor burst from irregular patches, creating chaotic off-axis forces. Because the nucleus rotates, these jets tilt, pulse, and misalign. The result? A measurable wobble. 3-dimensional acceleration in radial, transverse, and out-of-plane directions. Every real comet behaves like this. They spin, they tumble, they flicker. Their thrust vectors dance across the celestial stage. 3IATLAS does not dance. For over 20 consecutive days, it has exhibited sustained acceleration with perfect planar confinement. Not a single measurable deviation out of the orbital plane. Its motion slices through space as if guided by a geometric constraint, as though every vector of thrust were pre-aligned with surgical precision. If this is outgassing, then it is the most disciplined outgassing event in the recorded history of observational astronomy. To maintain such flawless symmetry, the jets would need to be arranged in perfect geometric opposition, each one counterbalancing its twin, canceling vertical momentum while sustaining orbital propulsion. That is not how ice sublimates. That is not how comets behave. That is not how nature works, and yet no one is saying it aloud. Not in press releases, not in journals, not in official statements. The silence itself has become part of the mystery. Because when an object moves with mathematical precision in defiance of every known physical irregularity, the question stops being, what is it doing? And becomes who's or what us taught it how. The silence and the signal, the data is right there, public, time-stamped and updated in NASA's own JPL Horizons database. No leaks, no rumors, no conspiracies, just numbers. Numbers that no one is acknowledging. Avi Loeb, who has never shied away from cosmic controversy, has said nothing. NASA Public Affairs, silent. No press briefings, no interviews, no technical notes. It sits there like a loaded gun in an unlocked drawer, visible to anyone who knows where to look, and somehow, no one is looking. Why? The simplest answer, the model isn't final. The orbit is still being refined as new data comes in. 3IATLAS has been receding from the Sun, reappearing in the night sky, its light curve and astrometric precision improving daily. By late November through January, we'll have the definitive trajectory, and with it, the verdict. If the A3IATLAS parameter vanishes, then it was a temporary artifact, a mirage caused by sparse data during the comet's solar conjunction. But if it doesn't, if the A3.0 persists through December and beyond, then we are watching something that should not exist, an object maintaining sustained directional thrust in 2 dimensions with perfect null motion in the third. That is not a comet. That is control. Now combine this with the anonymous post, a researcher claiming access to internal ESA datasets, describing an object venting matter symmetrically from an internal energy source. A cue ball, they said, a relic of the early universe, a macroscopic quantum engine producing isotropic ablation, uniform outflow, no recoil, no thrust. But wait, the JPL data shows thrust, radial and transverse acceleration. How can both be true? Here's how. If the core truly is a cue ball, a perfect spherically symmetric engine boiling matter outward evenly, then the mantle, the outer shell we see, need not be perfectly uniform. Even the faintest surface irregularities, a denser ridge here, a pocket of carbon dioxide there, would let sunlight and solar wind exert microscale pressure imbalances. The symmetry of the core would remain intact, but the interaction with the solar environment could bias the ejected flow, creating the appearance of controlled planar thrust. The geometry fits, the equations fit, the timing fits. 2 entirely independent datasets, one anonymous, one official, now describe the same impossible phenomenon. So we arrive at a moment of quiet dread. If this holds through the next observation window, if 3IATLAS continues to move as though guided by invisible hands, then we are not looking at a comet at all. We are looking at the first visible fragment of dark matter, a living equation still burning from the birth of time. 1. The core argument. A10, A20, A3.0. These are the components of non-gravitational acceleration in orbital mechanics. A1, radial, toward or away from the sun. A2 bas or transverse, along the orbit path. A3, normal, out of the orbital plane. For 3IATLAS, A1 and A2 show sustained thrust-like behavior, consistent with an active or self-propelling object. 3. 0 means no motion perpendicular to the orbital plane, which is not what natural jets or outgassing typically produce. That alone makes it extremely odd. 2. The cue ball hypothesis. The cue ball idea comes from speculative particle physics, a hypothetical, self-contained object made of scalar fields, capable of slow decay and isotropic, equal in all directions energy release. Here, the author ties that to 3IATLAS by saying, the core might release energy uniformly. The mantle, outer layers, is irregular and interacts with sunlight, creating small directional pushes. The result, small a1, small a2, 0 a3, exactly what the data shows. So the fit between theory and observation is suspiciously neat. For as what the silence suggests, the mention of Avi Loeb, known for theorizing about Oumuamua's artificial origin, NASA's lack of comment and data quietly available in JPL horizons, implies that this anomaly is real, but no one wants to say the words, this might not be a comet. It's a narrative tension, institutional caution versus independent analysis. Mass loss paradox to explain the observed acceleration via natural outgassing. The comet would need to have lost 5.5 billion tons of material, yet there's no corresponding debris cloud large enough to match that loss. So, acceleration without adequate mass loss. Unnatural propulsion or physics. 5. The test window. December 19, 2025. That's when 3IATLAS comes closest. 67 million kilometers inside Earth's observational comfort zone. Perfect for Hubble, James Webb, and ground telescopes to analyze whether its activity declines like a comet's, whether gamma rays appear, indicating internal decay, whether A3 remains 0, whether a debris cloud forms. These are falsifiable predictions. The author is framing this as a scientific test rather than pure speculation. 6. If the data holds, then we'd have sustained 2D thrust 0, out of plane motion, no visible mass, lost. Possible high energy emissions, all of which point to something that behaves like a controlled object and not a natural comet. The missing debris cloud if 3IATLAS truly lost 5.5 billion tons of material, as the outgassing hypothesis demands. Then there must be a visible debris field. Expanding gas and dust should create a bright, extended coma. The coma should glow in infrared and visible light, displaying clear spectral lines from CO2, carbon dioxide, H2O, water vapor, CO, carbon monoxide, CN, cyanide, Ni, nickel vapor. Yet, that cloud isn't seen. No massive plume, no expanding halo, nothing to match the physics. So the standard cometary explanation collapses. What remains are two extraordinary possibilities. A non-natural propulsion mechanism, i.e., internal energy source or engine. A new form of physics. Something beyond our current models of material behavior and celestial mechanics. 2. The anonymous 4chan post. The narrative introduces a wild card, an anonymous researcher claiming insider access. They describe a cue ball or macroscopic quantum object, a stable field configuration left over from the early universe. It emits symmetric isotropic energy, explaining 3IATLAS's acceleration without visible mass loss. They make specific, falsifiable predictions tied to dates and data, something real hoaxes rarely do. The credibility here isn't in authority, but in coherence. The theory matches NASA's data, the A1-A2 acceleration pattern. It predicts observable outcomes in December, and it displays deep interdisciplinary understanding, particle physics, cometary thermodynamics, and orbital dynamics. That makes it worthy of scientific attention, even if it sounds extraordinary. 3. Where we stand. November 4th, 2025. 3IATLAS is behind the Sun, hidden from Earth-based telescopes. It will reappear around November 11th. In the pre-dawn sky, Mars orbiters, especially the high-rise camera aboard NASA's Mars Reconnaissance Orbiter, captured it in October when it passed just 30 million kilometers from Mars. Those images have not been publicly released. That detail adds tension. Why hold back the data? Though in real astrophysics, image calibration and data embargoes are common, but the mystery tone here is deliberate. 4. The stakes of December 2025. By mid-December, the comet will be close enough to Earth, 267 million km, for high-resolution spectroscopy by Hubble and Webb. Astrometric tracking to test the A3/0 anomaly, gamma ray, and optical observations to detect unusual emissions or isotropic decay. It's the moment of truth, the universe's own experiment. If the object fades and behaves like a normal comet, hypothesis rejected. If it doesn't fade, doesn't lose mass, and continues to accelerate directionally, we've found something else. First, the implication, a macroscopic quantum object. If the cue ball hypothesis holds, IATLAS isn't a comet. It's a macroscopic relic from the early universe, stable for billions of years. It would be direct evidence that dark matter has structure, not just invisible particles, but massive, complex, self-stabilizing objects. That would mean dark matter interacts with baryonic matter, ordinary matter, in measurable ways. These structures may be common, drifting unseen through the galaxy until our instruments improve. And if we found one so soon after activating a new survey telescope, the implication is chilling. The galaxy could be full of them. In summary, this passage closes the loop between mystery and cosmology. Empirical tension, no debris. Cloud. Theoretical boldness, cue ball framework. Institutional. Silence, no public comment. Predictive. Science, wait until December. It's written like a scientific thriller, where each anomaly is a breadcrumb, leading toward a possible rewriting of physics itself, the dark matter visitors, and, if the galaxy truly is seeded with massive dark matter objects, vast, silent bodies drifting through interstellar space on trajectories that seem too precise to be random, then we must ask a different kind of question. How many have passed through our solar system before? How many are here now, invisible, undetected? And most unsettling of all, what happens when one comes closer than 3IATLAS did? Because if a cue ball the size of 3IATLAS, 33 billion tons of exotic matter, moving at 60 kilometers per second and never struck Earth, it would not carve a crater. It would redraw the map of the planet, an extinction-level event, arriving without warning because such objects are invisible until they near the sun, until they begin to outgas. And by then, if their path crosses ours, it is already too late. This is not fear-mongering. This is risk assessment. If cue balls are real and if they are common, they represent a class of cosmic hazard we have never prepared for. Not asteroids. Not comets, but something denser, faster, and darker than both, hidden until it's already here. Our planetary defense systems were never designed to detect this. Our telescopes, our algorithms, our response protocols, all calibrated for what we can see. But these things, we wouldn't know they exist until the universe decides to show us. And now, the countdown begins. 45 days. 45 days until December 19th, when we'll finally see if there's a debris cloud. 45 days until Hubble, Webb, and every major observatory on Earth turns toward this mystery. 45 days until the gamma-ray detectors search for that 73-megawatt signature. 45 days until we know, once and for all, whether we are looking at an ordinary comet, or at something that should not exist. And if it should not exist, then we are forced to ask the question that changes everything. If this is real, what else is out there? What else have we been calling dark matter for the last 90 years, never realizing that it might have shape, structure, and the quiet, terrible ability to wander into our neighborhood whenever it wants? The leak NASA didn't want you to see. The real leak isn't the 4chan post. The real leak is the JPL Horizons data, that quiet little number tucked away in the orbital solution. A3IATLAS. That number is public, verifiable by anyone. It's also impossible for a natural comet. Someone noticed. Someone pulled the data set, and when they shared it, the silence began to fracture. Because if that number holds, it means the models are lying. And if the models are lying, then in 45 days, when the new observations come in, when predictions either hold or fail, no official denial will matter. The data will speak for itself. And if the data says cue ball, then we are living in a universe stranger and far more dangerous than we ever imagined. What happened behind the sun October 29th, 2025, perihelion. 3IATLAS reached its closest approach to the sun, 1.36 astronomical units, roughly 203 million kilometers of separation. For 8 days before and several after, the object was lost in the solar glare, a period of solar conjunction, where even our most powerful telescopes could not track its behavior. And in those invisible days, something changed. When 3IATLAS re-emerged in early November, astronomers noticed it instantly. Its brightness curve was off. The object had accelerated. And strangest of all, its color had shifted, not enough to scream artificial, but enough that everyone watching it stopped pretending this was routine. The ALMA evidence. Let's start with what we know. On October 29th, the Atacama Large Millimeter Array, ALMA, was monitoring 3IATLAS as closely as the geometry would allow. ALMA doesn't see light the way our eyes do. It works in millimeter and submillimeter wavelengths, able to pierce through solar glare that blinds optical instruments. The result? A subtle but shocking anomaly. When ALMA processed its tracking data, 3IATLAS wasn't where it was supposed to be. It was off by 4 arcseconds in right ascension, 4 arcseconds, a tiny angle on paper. But at the object's distance from Earth, that offset translates to thousands of kilometers. Thousands of kilometers off course, in a trajectory that should be dictated only by gravity and outgassing physics. The models said it couldn't happen. The universe said it just did. The acceleration problem: comets deviate from purely gravitational orbits all the time. This is not new. Outgassing creates thrust. Jets of sublimating ice and gas push the nucleus around, producing small but measurable shifts in trajectory. That's why orbital models include non-gravitational acceleration parameters in the first place. So far, nothing about 3IATLAS should be surprising. At perihelion, when solar heating is at its peak and volatile compounds sublimate most rapidly, that's exactly when we expect the strongest deviation from a purely gravitational orbit. So the timing of the anomaly fits a natural cometary process, but the magnitude does not. Within hours of seeing the ALMA deviation data, Avi Loeb ran the numbers. If 3IATLAS's acceleration were produced solely by the rocket effect of gas venting off its surface, then conservation of momentum gives a simple relationship: force, mass loss rate, x, velocity of the expelled gas. That force drives the acceleration. The comet's total mass determines how much that acceleration changes its speed. When you solve for the mass loss rate, you get a number, and that number is staggering. To produce the observed acceleration, 3IATLAS would need to lose roughly 10% of its entire mass in the span of 1 month. If its total mass is about 33 billion tons, the conservative, lower estimate, then it must have ejected around 3.3 billion tons of material during its passage near the Sun. That mass doesn't disappear. It has to go somewhere. It should form a coma, a vast diffuse cloud of gas and dust surrounding the nucleus, scattering sunlight, glowing faintly, and producing a rich spectrum of emission lines. Carbon dioxide, water, carbon monoxide, cyanide. In nickel vapor, everything we've already detected coming off the object should, together, create a cloud so large and bright it would be unmistakable to any telescope that looks its way. December 19th. That's the date when we'll know. IATLAS will make its closest approach to Earth, 267 million kilometers in Tycho and Hubble. Webb and hundreds of ground-based observatories will have their best window to observe it directly. If the coma is there, vast, luminous, and impossible to miss, then the data confirms what physics predicts. A natural process. Exotic chemistry, possibly. Unusual composition, definitely. But still a comet, behaving according to known principles. If the cloud isn't there, then we have a problem, a serious one. Because if the acceleration wasn't caused by outgassing, then something else is pushing it, internal propulsion, directed energy, a mechanism we do not yet have a name for. This isn't speculation. It's the only logical conclusion the data allows. Either the mass was ejected and we'll see the cloud, or the mass was not. And if the mass was not, then something unnatural is at work. There is no third option. The color anomaly. Now we need to talk about the color, and this is where the story gets murky. Unlike the acceleration data, the color observations are not clear-cut, and they're much harder to verify. Multiple sources, and including Stereo A, SOHO, and GOES-19, were monitoring the region around the Sun during late October. In the processed images from these solar observatories, 3IATLAS appeared to brighten sharply as it approached perihelion. That part makes sense. Comets brighten as they near the Sun. More sunlight means more scattering off dust and gas. But what didn't make sense was the spectrum. Comets are usually redder than the Sun. That's textbook physics. Dust scatters sunlight, and scattering removes blue wavelengths first. It's the same reason sunsets glow red. Short wavelengths get scattered away, leaving only the long, red light to reach your eyes. But according to some early analyses of the solar observatory data, 3IATLAS wasn't red. It was neutral, even slightly bluer than the Sun itself. Not dramatically so, not glowing electric sapphire like some sci-fi drive core, but enough to raise eyebrows among scientists who've been tracking comets their entire careers. If that measurement holds up, and it's a big if, because the data is noisy and the instruments weren't designed for this, then it demands an explanation. Avi Loeb suggested 3 possibilities. Option 1, massive evaporation. If the object were losing material so violently that the coma was dominated not by dust, but by freshly sublimated gas, and if that gas was being ionized by the Sun's radiation, then you could get blue emission lines, particularly from ionized carbon monoxide, which radiates strongly in the blue-violet part of the spectrum. It would be extreme, but still within the bounds of natural physics. Option 2, an internal light source, a hot engine. This is the one that grabs headlines because it's provocative. If 3IATLAS contains some internal energy mechanism, something radiating in the visible spectrum at temperatures comparable to or hotter than the Sun's surface, then it would naturally emit blue-shifted light. That's just blackbody radiation. The hotter something is, the bluer it glows. But this explanation carries a heavy implication. The object would have to be artificial, or at least powered by a non-natural energy process. Option 3, and this is the one Loeb calls most plausible. If the anomaly is real, is that the observation itself is being misread. Instrumentation artifacts, calibration drift, scattering geometry, 1,000 small things can conspire to trick the data into lying. And yet, if the color really did shift toward blue, then something extraordinary happened behind the Sun. something that changed the way this object interacts with light itself. The perihelion Enigma solar observatories were never meant for this. They were designed to study the sun, not to perform precision photometry on faint comets skimming its blinding halo. Instruments like SOHO Stereo and GOES 19 are built to dissect the corona, not to capture a dim, wandering speck lost in a flood of solar fire. In their field of view, 3IATLAS is little more than a ghostly smudge, buried under the glare of the sun. To even see it, scientists have to push their data to the limit, subtracting overwhelming background light, enhancing contrast, and stacking frames until something faint emerges. But that kind of image processing comes at a cost. When you start bending data that far, artifacts begin to masquerade as signals. A blue hue might not be real at all. It might be the product of filter mismatches, varying exposure times, or subtle calibration errors between instruments that were never designed to work in unison. Until we have high-quality spectra from Hubble or JWST in December, the color anomaly remains a question mark. Suggestive, intriguing, but inconclusive. What is conclusive is the acceleration. The ALMA data holds, the JPL orbital solution holds. No matter how you slice the math, 3IATLAS deviated from a purely gravitational path during perihelion. That is not up for debate. The only question is why, and that's where the timing becomes everything. Perihelion, the moment of closest approach to the sun, is also the perfect moment to perform a propulsion maneuver. Space engineers know it as the Oberth effect. If you fire an engine when you're moving fastest, you extract the maximum possible change in kinetic energy from the same amount of thrust. The deeper you dive into a star's gravity well, the faster you move, and the more efficient your burn becomes. If you wanted to slow down, to shed velocity and drop into a bound solar orbit instead of slingshotting back into interstellar space, perihelion is when you do it. You fire your engines there. You make your move at the very edge of hell. Now here's the strange part. 3IATLAS is on a hyperbolic trajectory, an unbound orbit. It came from the stars, and it's on its way back out. But during perihelion, right at the point where a maneuver would make the most sense, we detected an anomalous acceleration. Is that proof of anything artificial? No. Comets are naturally most active at perihelion. That's when the sun's heat peaks. That's when outgassing surges and jets of vapor can push a nucleus off course. But the coincidence is hard to ignore. The acceleration happened exactly when an artificial engine burn would occur. It aligns perfectly with both a natural process and a deliberate act of course correction. It proves neither, yet echoes both. And when you start to stack enough of these coincidences, each one plausible, each one explainable, but all lining up just a little too neatly, you eventually have to ask the uncomfortable question. Are they really coincidences? The hidden window, the geometry was unforgiving. By late October, 3IATLAS had slipped almost directly behind the sun from Earth's perspective. Solar conjunction occurred on October 21st, and for roughly 2 weeks from mid-October to early November, the object vanished from view. No ground-based telescope could track it. It was lost in the solar glare. At the very moment when its trajectory bent closest to the sun, the most critical phase of its passage, we were effectively blind, and that raises a deeply uncomfortable question. If you were designing an interstellar probe and you wanted to perform a maneuver, a data transmission, or anything that might draw attention, and you wanted to do it without being observed by the inhabitants of the third planet, when would you choose to act? You'd do it when that planet couldn't see you. You'd do it at perihelion, when your orbit naturally carries you behind their star. You'd do it during solar conjunction. Now none of this is proof. It's just geometry. A natural comet has no agency in its trajectory. It follows the orbit dictated by celestial mechanics, set millions, perhaps billions, of years ago when it was first ejected from its home system. Its timing is coincidence, nothing more. The odds that perihelion and solar conjunction would coincide from Earth's point of view are roughly 1 in 4, depending on orbital inclination. Not suspiciously rare, just interesting. But if the trajectory was chosen, if it was planned, then the timing becomes perfect. Approach the inner solar system along the ecliptic, skimming past multiple planets. Time your closest solar approach to coincide with the one interval when the most advanced observers, us, are forced to look away. Use the sun itself as a shield. a wall of blinding radiation between your operation and their instruments. Then emerge on the other side, outward bound, trailing gas and dust, wearing the perfect disguise, a comet, unless someone checks the math. Unless someone looks close enough to see that the data doesn't quite fit. This is what's being called the Trojan horse hypothesis, the idea that Atlas presents every outward sign of being a natural comet, outgassing, spectral lines, a coma, and yet those features may be incidental or worse, deliberate camouflage for something far more complex beneath the surface. Dr. Lowe has been clear on this point. We should not judge the object's nature by the vapors escaping from its crust, any more than we should judge a book by its cover. The core mystery, the surface chemistry, tells us only what's on the outside. It does not reveal what lies beneath. If the core of 3IATLAS is a cue ball, a dense nugget of exotic matter left over from the earliest moments of the universe, then its icy, comet-like mantle is just debris, accumulated over billions of years drifting through interstellar space. That outer shell behaves like a comet because it is made of the same stuff comets are made of: volatiles, dust, and organic compounds. When sunlight heats it, it sublimates. It forms a coma. It looks exactly like a comet, but underneath the core is something else entirely, something with its own internal energy source, something that does not respond to solar heating because it has been stable for billions of years. The same logic applies if the core is artificial. You wouldn't build an interstellar probe out of conventional metal and electronics and send it across the galaxy. Radiation, collisions, and the sheer timescale would destroy it. Instead, you build it out of ice. You coat it in a thick, protective shell of frozen volatiles that can absorb impacts, self-heal, and provide shielding. When it approaches a star, the shell sublimates. It acts like a comet, looks like a comet until you examine the details closely enough to see the inconsistencies. Both the cue ball scenario and the artificial probe scenario predict the same outcome. A comet-like exterior, anomalous properties beneath, mass that doesn't add up, unexpected chemistry, strange thermal behavior, a trajectory that defies simple mechanics, and critically, acceleration without a matching debris. Cloud December 19th will be decisive. If a massive coma, billions of tons of gas appears, the natural explanation holds. If it does not, one of the alternative hypotheses moves from speculative to necessary. We won't have to guess. We won't have to argue probabilities or statistics. We will have direct observational evidence, one way or the other. In the meantime, what do we do with the perihelion data? We have the anomalous acceleration. We have the possible color anomaly. We have perfect timing for a covert maneuver. We have institutional silence. And we have 6 weeks until the critical test. The smart course of action is clear. Wait. Collect more data. Reserve judgment until the observations tell the story. The dilemma of caution. A responsible scientist would say this: do not jump to conclusions. Do not overinterpret noisy preliminary results from instruments never designed for this type of measurement. Peer review demands skepticism. Caution. Wait for the evidence. And yet here is the problem. If 3IATLAS is not natural, if it is a cue ball or a probe or something entirely unknown, then waiting may be the wrongest thing possible, because it will not wait for us. It is on a hyperbolic trajectory. It is leaving. By March 2026, it will pass Jupiter and head toward the outer solar system. By late 2026, it will be too distant, too faint, for most telescopes to track. We have a limited window, and if we squander it with caution, we may never get another chance to study an object like this up close. The dilemma is stark. Act too fast, and you look foolish if December's debris cloud proves 3IATLAS is just a weird natural comet. Act too slow, and you miss the opportunity to confirm something extraordinary. There is no perfect choice, only trade-offs. Here's what we can say with certainty. The perihelion data is weird, not definitive, not undeniable, but enough to make outright dismissal premature. The object accelerated at exactly the moment a controlled maneuver would be most effective. Spectral measurements hint at anomalies beyond passive solar heating. The trajectory placed perihelion behind the sun from Earth's perspective. Mass estimates demand either a statistically impossible natural object or something entirely unnatural. None of this is proof. But all of it is consistent with the hypothesis that 3IATLAS is not what it appears to be. Consistency matters. When multiple independent lines of evidence point in the same direction, even if individually inconclusive, the aggregate weight cannot be ignored. So we wait. 6 more weeks. December 19th. Closest approach. The best observational window. The definitive test of the debris cloud hypothesis. And potentially the key to discovering whether 3IATLAS is simply a comet or something far stranger. Watching the data trickles in until December 19th. All we can do is watch the data trickle in and see whether the anomalies grow stronger or fade away. But if I had to bet, based on everything we know so far, here's my wager. No massive debris cloud. When Hubble and James Webb train their eyes on 3IATLAS in mid-December, they will likely see a faint coma, consistent with low-level outgassing. Nothing close to the billions of tons required to account for the observed acceleration. When that happens, the conversation will change dramatically. We will have exhausted natural explanations. 10 impossibilities. Avi Loeb is not a fringe scientist. Frank B. Jr., professor of science at Harvard University. Former chair of the astronomy department. Director of the EO. Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. Former chair of the Board on Physics and Astronomy of the National Academies. Author of hundreds of peer-reviewed papers, this is someone whose reputation is built on decades of rigorous work, not someone who makes wild claims for attention. And yet he is saying that 3IATLAS displays properties that challenge everything we know about natural objects. He has compiled a list, 10 anomalies. Each one individually is strange. Together, they form a pattern that is hard to dismiss. Anomaly. 1. Retrograde trajectory aligned with the ecliptic plane. Probability 0. 2%. 1 in 500. The ecliptic plane is the flat disk where the planets orbit the Sun. Defined by Earth's orbit, it contains nearly all the major planets, which formed from the same rotating disk of gas and dust 4.6 billion years ago. Objects originating in our solar system generally orbit within or near this plane. Oort cloud comets, on the other hand, arrive from a roughly spherical shell surrounding the solar system. Their approach directions are random, some prograde, some retrograde, some highly inclined. IATLAS is retrograde, moving opposite to the planets. Fine. About half of Oort cloud comets are retrograde, but here's the kicker. It is aligned within 5 degrees of the ecliptic. It is moving backwards along the plane of the planets. For a randomly oriented interstellar object, the probability of that alignment is roughly 0. 2%. Not impossible, but unusually precise. You were about to say, we've only found 3 interstellar objects so far. Exactly. And 3IATLAS is already behaving in a way that pushes the boundaries of statistical expectation. Anomaly. 2. The sunward antitail 1 2 Boros, 3 3IATLAS. Finding 3 interstellar objects with one appearing unusual might seem unsurprising. 1 in 500 odds mean you would expect to see something like this once every 500 objects. But we have only seen 3. This could be statistical noise, except the other anomalies don't disappear. They stack. Anomaly. 2. Sunward. Anti-tailmost comets have tails that stream away from the sun. Solar radiation pressure pushes dust outward. The solar wind sweeps ionized gas along. Occasionally, due to viewing geometry, a comet may appear to have a tail pointing sunward. This is called an anti-tail, but it is always an optical illusion. You're just looking edge-on at the dust trail. IATLAS is different. Multiple instruments, Hubble, the KEK telescope, and others, observed a faint feature pointing toward the sun. Spectroscopic analysis confirms it is real emission, not a perspective trick. Material is being ejected sunward. How is this possible? The only way to blast material toward the sun is with a powerful jet on the sun-facing side. Carbon dioxide sublimates. High-pressure jets form. Material is expelled fast enough to overcome radiation pressure. This is not impossible, Some comets produce jets that occasionally point sunward. But here's the kicker. Jets form from localized active regions on a nucleus. The nucleus rotates. As an active region spins into and out of sunlight, the jet flickers, causing pulses in brightness and variations in the coma. ATLAS shows none of this. Its brightness is perfectly constant, measured over days by multiple observatories. If a jet is producing the sunward anti-tail, it is not attached to a rotating active region. It is coming from something that is always pointed at the sun. 3IATLAS. The interstellar enigma that defies probability, the nucleus of 3IATLAS presents a dynamical puzzle. Either it is not rotating, a bizarre scenario for a body that has drifted through space for billions of years, or the comet's jet is not anchored to any surface feature, somehow emanating uniformly across the entire sun-facing hemisphere. Neither explanation fits any known model of natural comet behavior. Anomaly. Number 3. Mass and velocity. IATLAS is colossally massive, 1 million times the mass of Oumuamua, 1,000 times that of Borisov, and moving faster than both. The combined probability of such a discovery? Less than 0.1%. To put this in perspective, we have detected 3 interstellar objects. The first, Oumuamua, was tiny, roughly 100 meters across. Borisov measured about 400 meters. 3IATLAS? At least 5 kilometers, possibly larger. That represents a jump of over an order of magnitude in size, translating to 3 orders of magnitude in mass, if interstellar objects follow the same size distribution as solar system. Odysseys, where small objects vastly outnumber large ones. The odds of spotting a giant object on our third detection are astronomically low, and that's not all. 3IATLAS is moving at 60 kilometers, faster than both predecessors. Oumuamua, 26 kilometers relative to the solar system. Borisov, 32 kilometers. 3IATLAS. 60 kilometers faster objects are harder to detect because they spend less time in the inner solar system, where telescopes are concentrated. Finding a fast, massive object is not just improbable, it's extraordinarily lucky. Some would even say, too lucky. Anomaly number 4. Arrival timing. The object's trajectory appears strangely tuned for close encounters with multiple planets. Closest approach to Mars. October 3rd, 29 million kilometers Venus. November 3rd, 97 million kilometers Jupiter. 2026. These are not impacts, and by cosmic standards, not even extremely close passes, but close enough for orbiting spacecraft to observe 3IATLAS directly, gathering invaluable data. Even more curious, its perihelion occurred behind the sun from Earth's perspective, creating a natural 2-week observational blackout during solar conjunction, October 21st. For 2 weeks, ground-based telescopes could not see it, hiding this cosmic anomaly in plain sight. IATLAS. Cosmic coincidence or impossible design. On the surface, 3IATLAS's perihelion timing isn't inherently suspicious. Roughly 1 in 4 objects on random trajectories will reach perihelion when Earth is on the opposite side of the sun. But combine this with its near passes to multiple planets, and the alignment starts to look far less random. Estimating the probability is tricky. It depends on what counts as a close pass and what timing window you consider significant. Yet Lowe's calculations, based on reasonable assumptions, give a 1 in 20,000 chance, 0.05%, that a randomly arriving interstellar object would line up this way with Mars, Venus and Jupiter simultaneously. Not impossible, just staggeringly unlikely. Anomaly. 5. Nickel dominates iron. Here, the object breaks another fundamental cosmic pattern. In our solar system, nickel and iron always appear together. Both are iron peak elements, produced in similar ratios during supernova nucleosynthesis. Even the most primitive meteorites, chondrites, consistently have a nickel-to-iron ratio of 6%. That means for every kilogram of iron, there's roughly 60 grams of nickel. This ratio is remarkably consistent across asteroids, comets, and reflects the composition of the solar nebula, essentially the raw material of the entire solar system. But 3IATLAS defies this rule. Its coma shows strong nickel emission, yet iron lines are completely absent. Despite iron being more abundant and easier to detect, multiple telescopes, including Keck, confirm these results. Even stranger, the nickel-to-cyanide ratio, is orders of magnitude higher than any known solar system comet, including 2I Borisov, the only other interstellar comet studied in detail. This isn't just unusual, it's chemically bizarre. If 3IATLAS truly formed in another stellar system, that system would need a drastically different nickel-to-iron chemistry than our own. Possible? Yes. Probable? Not by a long shot. Atlas. Chemistry and composition. That defy the laws of nature, stellar nucleosynthesis is remarkably consistent. The relative abundance of nickel and iron in the universe does not vary enough to explain 3IATLAS's extreme composition. This suggests the nickel is not coming from the bulk composition of the object, but rather from a localized process or a specific compound that preferentially releases nickel without releasing iron. One candidate, nickel tetracarbonyl, an organometallic compound where nickel bonds to 4 carbon monoxide molecules. When it decomposes, it releases pure nickel and carbon monoxide, no iron. But here's the catch. Nickel tetracarbonyl is synthetic. It's industrially produced on Earth. It is not known to form naturally in space unless there exists some exotic chemistry in protostellar disks capable of producing nickel tetracarbonyl, or unless the object is not natural. Anomaly. Douglas 6. Water content only 4% by mass. Normal comets are ice balls, with water ice dominating their volatiles. As they approach the sun, water sublimates, producing hydrogen and hydroxyl emission lines that define classic cometary behavior. Carbon dioxide is usually a minor player, typically 10–20% by mass. Atlas flips this expectation on its head. Observations from the James Webb Space Telescope and other instruments reveal a coma dominated by 87% carbon dioxide, while water makes up only 4%. This suggests one of two extraordinary possibilities. The object formed in an extremely cold environment, cold enough for carbon dioxide ice to be more abundant than water ice. The object has previously passed close to other stars and lost most of its water, leaving only the last remnants of volatiles. But if it has been heated before, why is it still losing 150 kilos of material per second? And if it formed in a carbon dioxide-rich environment, what kind of environment could create such an object? Current models of protostellar disks do not predict comets with this composition. Anomaly. 7. Extreme negative polarization. When light scatters off dust particles, it becomes partially polarized. The degree and sign of polarization depend on particle size, shape, and composition. 3IATLAS exhibits unprecedented negative polarization, unlike any comet we've ever observed. The probability of this occurring naturally, less than 1%. Every new measurement seems to push 3IATLAS further beyond the bounds of known physics and chemistry, making it a cosmic enigma that refuses to fit any existing model. Atlas. Dust, polarization, and a cosmic coincidence? Most comets display positive polarization, meaning scattered light has more electric field vibrations perpendicular to the scattering plane than parallel. This aligns with expectations for typical cometary dust, which consists of irregular grains of silicates, organics, and other materials. Atlas defies this rule. At a phase angle of just 7 degrees, the polarization reached 2.7%, an extreme negative value unprecedented among all known comets. Even 2I Borisov never came close. To produce this effect, the dust particles must possess highly unusual optical properties. Large and porous and complex internal structure capable of scattering light in a way that flips the polarization. The anonymous 4chan post described the dust as black and porous, like smoke, large and incredibly complex, a description that matches the properties needed to explain the polarization, but also matches engineered materials such as aerogels or carbon nanostructures designed for lightweight insulation or radiation shielding. Is this proof of artificial origin? No. Nature can produce fractal aggregates, porous organic matrices, or complex coagulated grains. But the fact that the dust possesses exactly the properties you would want if designing a thermal shield or lightweight protective material is, at minimum, highly intriguing. Anomaly. Great. Arrival direction within 9 degrees of the WOW. Signal in 1977. The Big Ear radio telescope at Ohio State University detected a strong, narrowband signal lasting 72 seconds, near the hydrogen line frequency, considered by many SETI researchers as an optimal interstellar call sign. Astronomer Jerry Amon famously circled the printout and wrote, "Wow," giving the signal its name. Despite decades of follow-ups, the signal has never been observed again. Accounting for Earth's rotation and the telescope's beam pattern, the direction of the WOW signal points to a region in the constellation Sagittarius, and 3IATLAS's arrival vector lies within 9 degrees of that same region. The probability of such an alignment occurring by chance? Roughly 0.6%. Coincidence, perhaps. But when combined with the dust anomalies, chemical oddities, and improbable trajectory, it adds yet another layer to an already baffling cosmic puzzle. 3IATLAS trajectories brightening, and the acceleration mystery. When astronomers trace 3IATLAS's trajectory backwards through the galaxy, it appears to originate from a direction within 9 degrees of the WOW signal region. 9 degrees is not pinpoint precision, but it's close enough to catch attention. The probability that a randomly arriving interstellar object would come from this region? About 0.6%. Not astronomically small, but when an object already defies so many expectations, even this coincidence is intriguing. Could there be a connection? Almost certainly not. The WOW signal was likely terrestrial interference or some transient astronomical event. And even if it were an extraterrestrial transmission, the odds that the same civilization would send both a radio signal and a physical object to Earth simultaneously are vanishingly small. Yet, as anomalies accumulate, coincidences begin to stack in an uncanny way. Anomaly number 9. Rapid brightening and unusual color. Near perihelion late October. Observations from solar observatories revealed that 3IATLAS brightened faster than any known comet as it approached perihelion. The brightness scaled approximately with distance to the Sun raised to the power of 7.5 plus or 1, an extremely steep dependence. For context, most comets brighten roughly as 1 distance 2, maybe 1 distance 3 for exceptionally active ones. Brightening proportional to 1 distance 7 is an order of magnitude steeper, indicating the object was releasing enormous energy as it neared the Sun, either through massive sublimation of volatiles or via some other unknown process. Preliminary data also suggests that the color shifted in ways that dust scattering alone cannot explain. If these observations hold, we may be seeing either extreme cometary activity or an entirely new phenomenon. The brightening could fit a natural explanation, massive outgassing. But it is also consistent with an internal energy source ramping up in response to solar heating, which fits alternative, more exotic explanations. Anomaly. 10. Non-gravitational acceleration. Without a corresponding debris cloud, this is the anomaly that remains unconfirmed but deeply troubling. Acceleration is solid, JPL Horizons data shows it, and ALMA observations confirm it. What is missing? Confirmation of a massive debris cloud, which would normally explain the acceleration. The final piece of the puzzle arrives in December, when observations will clarify whether a debris cloud exists. If it does, this anomaly vanishes. If it doesn't, we are left with an object accelerating in space with no apparent physical cause. One more mind-bending violation of expectations. Atlas, when probabilities collapse. If the debris cloud does not exist, this becomes the most significant anomaly of all. At that point, we have an object accelerating in space without ejecting the mass required to produce that acceleration. A scenario that flatly contradicts classical physics, unless some unknown mechanism is at work. Now let's talk about probabilities. Each anomaly observed in 3IATLAS carries an associated likelihood, some less than 1%, some fractions of a percent, and a few below 0.1%. These represent the odds that a random natural object would display each property. What are the odds that a single object displays all 10 anomalies? If they were independent, you would multiply the probabilities, 0.2%, 0.6%, 0.1%, and so on. The product is astronomically small, on the order of 10, 15 or smaller, effectively 0, but the anomalies are not independent. Trajectory affects arrival timing. Composition affects brightness and chemistry. You cannot simply multiply them and claim a meaningful result. Yet even after accounting for correlations, the joint probability remains vanishingly small. No formal calculation has been published, because doing so properly would require a detailed covariance model, which we do not yet have. Qualitatively, though, the odds are low. low enough that dismissing 3IATLAS as just a weird comet starts to feel unsatisfying. This is where Bayesian reasoning comes into play. Start with a prior probability. Before observing any data, what are the odds that an interstellar object is artificial or exotic? Most would say extremely low. 1 in a million, 1 in a billion. The galaxy is vast, space is mostly empty, and the chance of encountering an alien probe or exotic relic passing through the solar system is minuscule. Then the data arrives. Under the natural comet hypothesis, the likelihood of observing all 10 anomalies is extraordinarily low. Under the artificial or exotic hypothesis, the likelihood is higher because these scenarios specifically predict unusual properties. Applying Bayes' theorem, the posterior probability shifts. It may not make the alternative hypothesis likely, but it moves it from absurdly implausible to merely implausible, and implausible things do happen. 1 in a million events occur all the time if the number of trials is sufficiently large. The question then becomes, have we observed enough trials in the galaxy to make this one object significant? 3IATLAS challenges us to ask the hard question. When anomalies stack in ways that defy our expectations, how do we interpret the universe's rarest phenomena? 3IATLAS, one-time opportunity or cosmic coincidence? How many interstellar objects pass through the solar system without being detected? If the answer is thousands or millions, finding one weird object isn't surprising. But if the answer is only a few per decade, then spotting a bizarre object on our third detection is suspicious. The truth? We don't know yet. The Vera Rubin Observatory promises to clarify. It's designed to detect interstellar objects at a rate of roughly 1 every few months. By the end of the decade, we may have dozens, maybe hundreds, of detections. If most are mundane and 3IATLAS remains the only weird one, then it was just a statistical fluke, a 1 in a million comet that happened to be one of the first 3 we observed. But if more anomalies show up, if these strange behaviors are not rare, then the problem becomes profound. We would have to explain why a significant fraction of interstellar objects defy our models. And at that point, alternative explanations stop being fringe speculation and start being scientifically necessary. For now, all we can say is this: Atlas is weird. Quantifiably, measurably weird. Its weirdness isn't proof of anything, but it demands serious attention. And that means using the best instruments we have while we still can. By the end of 2026, the comet will be too distant to observe. By the end of the decade, it will be just another faint dot among the stars, if we can even track it at all. This is not a laboratory experiment we can repeat. This is a one-time cosmic event, a singular opportunity to study an object that might be extraordinary, or might be a comet with strange chemistry. Either way, we need to investigate all 10 anomalies, 10 reasons to pay attention, 10 questions demanding answers. December 19th gives us at least one answer. The rest will take time, but the clock is running. And then there's the pop culture angle. On November 2nd, 2025, Kim Kardashian tweeted NASA, "Wait, what is the T on 3IATLAS?" The tweet went viral instantly, reaching millions of impressions within hours. Major news outlets picked it up. Suddenly, an obscure interstellar comet, previously discussed only in academic circles and niche astronomy forums, was headline news. NASA's acting administrator, Shaw Duffy, responded the same day. Great question. NASA's observations show this is the 3rd interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. Short, dismissive, reassuring. Exactly the kind of response you expect from a government agency trying to avoid speculation, and exactly the kind of response that fuels speculation. Kim Kardashian asking about 3IATLAS is not random celebrity nonsense. She has 400 million followers across platforms. When she asks a question, people pay attention, and the question she asked is exactly the one everyone should be asking. What is going on with this object? Why is it strange? Why are scientists arguing about it? And why does it feel like we aren't getting straight answers? Dr. Lowe responded sincerely, saying he would love to bring Kardashian up to date on all the anomalies of 3IATLAS. At this point, public attention is one of the few forcing functions capable of pushing institutions to release data and answer questions. If millions of people are asking why high-resolution images haven't been released, it becomes harder to ignore the question. And that brings us to the high-resolution problem. On October 2nd and 3rd, 2025, The high-rise camera aboard NASA's Mars Reconnaissance Orbiter captured images of 3I-ATLAS as it passed within 30 million km of Mars. High-rise and the vanishing images of 3I-ATLAS. The high-rise camera aboard NASA's Mars Reconnaissance Orbiter is the most powerful camera ever sent to another planet. It has an angular resolution of 1 microradian, translating to about 30 centimeters per pixel when imaging the Martian surface from orbit. Pointed at 3I-ATLAS from 30 million km away, that resolution corresponds to roughly 30 km per pixel. 30 km per pixel is not enough to resolve the nucleus directly. If the nucleus is 5 km across, it would appear as a tiny fraction of a single pixel. But it is enough to measure the brightness distribution of the coma, detect whether the glow around the nucleus is symmetric or asymmetric, identify jets or features invisible in lower resolution images. Obtain the best constraints yet on total brightness, allowing inferences about the size and albedo of the nucleus. By comparison, the Hubble Space Telescope imaged 3I-ATLAS on July 21st from a distance of 570 million kilometers, achieving a resolution of about 100 km per pixel. Good, but not great. The high-rise images, taken from 20 times closer, should have 3 times the resolution, revealing details Hubble could not. They should be the best images we will ever have of this object before it reaches Earth in December. Except, they haven't been released. It has been over a month. No publication, no press release, no data dump to the Planetary Data System, where NASA archival data is normally made public. Dr. Lowe requested access directly from Professor Alfred McEwen, the principal investigator of the high-rise camera team at the University of Arizona. No response. Congresswoman Anna Paulina Luna submitted an official letter to NASA, citing the scientific importance of the images and the public interest in understanding 3I-ATLAS. As of November 4th, still no response, still no images released. Why? The official explanation, as far as it exists, is the government shutdown. In early October, the United States entered a partial federal shutdown due to a budget impasse. Many NASA employees were furloughed, normal operations were disrupted, and data processing pipelines that usually run automatically were paused. The high-rise team, like many others, was operating with reduced staff and limited resources. Plausible? Yes. Government shutdowns mess things up. Timelines slip. Data releases get delayed. It happens. But for an object as weird, anomalous, and scientifically significant as 3I-ATLAS, every day that passes without access to these high-resolution images feels like a missed opportunity to answer questions that may never come again. The high-rise data dilemma, but here's the problem. The government shutdown ended weeks ago. Operations have resumed. Other Mars missions released data during and after the shutdown. ESA's Mars Express and ExoMars Trace Gas Orbiter released their images of 3I-ATLAS within days of taking them. Those images were lower resolution than high-rise, but they were released publicly with minimal delay. So why is high-rise different? One possibility: the data is still being processed. Raw images from spacecraft are not immediately usable. They must be calibrated, flat-fielded, corrected for instrumental artifacts, converted from digital numbers into meaningful physical units like radiance or reflectance. This takes time, especially if the target is unusual or if the observation was not part of the standard imaging sequence. High-rise was designed to image the Martian surface, not faint comets millions of kilometers away. Processing images of 3I-ATLAS might require custom calibration procedures, and the team could still be working on it. Fine, that's plausible. But if this is the reason, communicate it. A simple statement like, "We have the data. We are processing it. It will be ready in X weeks," would diffuse speculation. Instead, there is silence. Another possibility. The images show something unexpected, perhaps a feature that doesn't fit the comet model, or brightness measurements that are way off from predictions, or even hints that the object is not what it appears to be. If so, the team may be exercising extreme caution, running additional checks, consulting colleagues, and ensuring they do not release data prematurely. From a scientific standpoint, caution is good. Peer review is good. You do not want to claim something extraordinary only to discover it's a sensor artifact or a speck of dust, but there's a line between caution and obstruction. When the data, source were publicly funded, collected by a spacecraft paid for by taxpayers, and of high public interest, the balance shifts. The default should be transparency, not secrecy. Or perhaps the delay is purely bureaucratic. NASA has formal procedures for data releases, approvals that require multiple levels of management sign-off. These processes exist for good reasons, but they are slow. Combine that with a government shutdown, a controversial target, and high public attention, and delays compound. It is entirely possible that the high-rise images are sitting on a server, fully processed and ready, waiting for someone to click the final approval button, and that person is either too busy, too cautious, or too uninterested to prioritize it. Any of these explanations could be true, or all of them together. The result is the same. 1 month after the observation, we still do not have the data, and the longer the delay, the more suspicious it looks. To be clear, this is not an accusation of a cover-up. There is no evidence of a conspiracy to hide alien technology. It is almost certainly a case of normal institutional dysfunction, unfortunate timing, and poor communication. But for a comet as anomalous and scientifically significant as 3IATLAS, the lack of transparency fuels curiosity, speculation, and frustration, and keeps all eyes on what could be the last chance to study this object up close. Perception, speculation, and what high-rise might reveal perception matters. When you have an object already generating speculation, when data that should be public is withheld, and when official responses are dismissive, you create a vacuum, and that vacuum gets filled with theories. Kim Kardashian asking, "What's the T on 3IATLAS?" is a symptom of that vacuum. People sense that something is off. They may not be able to articulate exactly what bothers them, but they feel the mismatch between the official narrative and the strangeness of the data. And when their questions are met with silence or dismissal, they ask louder. Congresswoman Luna's letter is another symptom. She's not a scientist. She's a politician responding to constituent interest. People are asking their representatives, why is NASA not being more transparent about 3IATLAS? By submitting her letter, she is forcing accountability. Whether it will result in faster release of the images is unclear, but the fact that it was necessary at all speaks volumes about how the situation is being handled. So what might the high-rise images show? We don't know. We won't know until they're released. But we can make educated guesses based on what high-rise can do and what we already know about 3IATLAS. What? Brightness. The total brightness of the coma will provide a better estimate of the cross-sectional area of scattering material. Comparing. This to Hubble and ground-based observations could reveal changes over time. Increased brightness, increased activity, stable brightness, consistent outgassing, decreased brightness, strange, because the object was closer to the Sun in October than in July, and proximity usually means more activity. Morphology. The shape and structure of the coma will tell us if the glow is symmetric or elongated, which could indicate a jet or directional outflow. Hubble observed a slight extension toward the Sun, the anti-tail. High-rise. Could reveal whether this feature is more pronounced, less pronounced, or if other jets appear that were invisible to Hubble. 3 size. If the nucleus is large and bright enough, high-rise might resolve it directly or measure the central concentration of light, corresponding to the nucleus plus the inner coma. This could tighten estimates of the solid body's size. Current estimates range from 5 km to 46 km, depending on albedo assumptions. High-rise could narrow that range dramatically. Color high-rise has multiple filters, not as many as Hubble, but sufficient for crude color analysis. Any unusual coloration in the coma might be detected, giving clues about the object's composition or activity. In short, the high-rise images could answer some of the most pressing questions about 3IATLAS. Is it behaving like a normal comet? Are there unexpected jets or features? Is the nucleus size and brightness consistent with predictions? Is the coma showing anomalous colors that hint at exotic chemistry or structure? Until we see the images, all of this remains speculation. But educated speculation, informed by the capabilities of the best camera ever sent to another planet, and every day the data is withheld, that speculation grows. The stakes of withheld data. This is directly relevant to one of the most pressing questions. Did 3IATLAS display a spectral anomaly at perihelion? Any single measurement would be valuable. All of them together would be invaluable. And yet, more than a month after the observation, we still don't have the data. The frustration is palpable among scientists, journalists, enthusiasts, and apparently even Kim Kardashian. Her tweet is funny on the surface. Reality TV star weighing in on astrophysics? It's easy to mock. But underneath the humor lies a serious point. Why does it take a celebrity with hundreds of millions of followers to draw attention to withheld scientific data? Why does it take a congressional inquiry to push for transparency? Why isn't this automatic? NASA's mission statement promises to share discoveries with the public. The agency has a long history of releasing data freely, often within days or weeks. The Mars Reconnaissance Orbiter has been operating since 2006, and tens of thousands of high-rise images have already been released. The procedure is well established. So why is this one image set different? Maybe it isn't. Maybe we are just being impatient. Perhaps in a week or two the images will quietly appear on the Planetary Data System website with no fanfare, no explanation, and we'll all feel silly for making a fuss. Or maybe the delay means something. Perhaps the images show features that require careful thought about presentation. Maybe there's an internal debate about interpretation. Perhaps someone high up in NASA decided that releasing images of a controversial object at a politically sensitive time, with a vocal Harvard professor speculating it could be alien technology, was not a good idea. Not because the images prove anything dramatic, but because they might be ambiguous enough to add fuel to a fire NASA would rather see extinguished. We don't know which explanation is correct, but one thing is certain: transparency is always the better policy. If the images show a normal comet, release them and say so. If they show something strange, release them and admit it is strange. If they are ambiguous, release them and let the scientific community debate their meaning, holding data back for any reason other than legitimate. Quality control erodes trust, and trust is hard to rebuild once lost. December 19th is now the deadline. That is when 3IATLAS makes its closest approach to Earth, offering the best opportunity for observation with ground-based telescopes. And when Hubble and JWST will take new images and spectra, time is running out. Every day of delay amplifies the mystery, the speculation, and the tension. The clock is ticking. By the time high-rise images are finally released, they might already be old news. If they come before December, they could guide observation planning for the Earth flyby. If they come after, they will be little more than a footnote. The clock is ticking. The window of opportunity is closing. Every day that passes without transparency feeds speculation and erodes confidence in the institutions tasked with leading this investigation. Kim Kardashian asking, "What's the T on 3IATLAS?" is not the problem. The problem is that she has to ask it all. The problem is that a legitimate question about a scientifically important observation is met with a two-sentence brush-off instead of a substantive answer. The problem is that data collected by a publicly funded mission is not being released in a timely manner, and no one in an official capacity seems willing to explain why. So here we are, 1 month after the Mars flyby. No high-rise images, no explanation. Just a growing sense that something is not being handled properly. Whether this is due to incompetence, caution, or something else entirely, the result is the same. Public trust erodes, speculation grows, and the story becomes less about the comet and more about the response to the comet. If there is a lesson here, it is this: transparency is not optional, it is essential. People are smart. They can handle ambiguity. They can handle uncertainty. What they cannot handle is silence. Silence implies concealment, even if none exists. And once that perception takes hold, it is nearly impossible to dislodge. NASA, if you are listening, release the high-rise images. Now. Do it with a clear explanation of what they show and what they do not. Do it before December. While the data can still guide observations, do it because it is the right thing to do. The T on 3IATLAS is simple. We do not yet have all the data we should have. And until we do, questions will keep coming. From scientists, Journalists, members of Congress, and yes, reality TV stars with 400 million followers. Because at the end of the day, this is not about celebrity gossip. This is about science. And science demands all the data, not just the parts that are easy to explain, not just the chemistry that seems ordinary. We are talking about anomalies that should not exist. Nickel tetracarbonyl. NiCO4, a colorless volatile liquid boiling at 43 degrees. Highly toxic, extremely reactive, and utterly unnatural in the context of a comet that has been drifting through space for billions of years. Until we see the images, until we have all the measurements, the story of 3IATLAS is unfinished, mysterious, and urgent, and the clock is still ticking. The compound that best fits the spectral data from 3IATLAS is nickel tetracarbonyl, and that, frankly, is a problem. Let's start with what we know. Multiple telescopes, including the Keck Observatory in Hawaii, have captured detailed spectra of the gas surrounding 3IATLAS. A spectrum is, in essence, a fingerprint of light, a map of the molecules that absorb or emit radiation at specific wavelengths. From that pattern, we can identify the precise chemical species present, often down to astonishing accuracy. When you aim a spectrograph at a comet, you expect the usual signatures: water vapor, carbon dioxide, carbon monoxide, cyanide, organic volatiles, the predictable chemistry of frozen ices warming in sunlight. But 3IATLAS breaks that pattern. Its spectrum is dominated by nickel emission lines, strong, bright, unmistakable. Nickel is present in the coma at concentrations far higher than any known comet. And iron, which should be there always paired with nickel in cosmic abundance, is missing, not faint, not ambiguous, simply absent, below the detection limit. This is backwards physics. Every meteorite ever analyzed, every asteroid sample, every bit of cosmic dust we've collected from the solar system, all show a near-constant nickel-to-iron ratio of roughly 6%. That ratio is imprinted by the universe itself, a legacy of supernovae and the cooling of the solar nebula. You do not get nickel without iron, unless something has deliberately, or under very unusual conditions, separated them. One of the only known ways to achieve that separation is through the formation of nickel tetracarbonyl, NiCO4. On Earth, it's made industrially, using the Mond process, invented in 1890 by Ludwig Mond. In this process, impure nickel is exposed to carbon monoxide gas at around 50-60 degrees C. The reaction produces a colorless, volatile gas, nickel tetracarbonyl, which can then be decomposed by heating to 200 degrees, yielding ultra-pure nickel metal. The method is efficient, elegant, and entirely artificial. In nature, nickel tetracarbonyl is almost unheard of. It doesn't form in volcanoes, hydrothermal vents, or any biological system. It requires a delicate balance of temperature, pressure, and chemistry that Earth simply doesn't provide. Could such conditions exist in space? Possibly so, but only barely. Interstellar clouds are rich in carbon monoxide and trace metals like nickel. Under rare and finely tuned conditions, nickel tetracarbonyl might form, freeze onto dust grains, and later be trapped inside a forming comet. It's a theoretical possibility, but one that demands near-perfect timing and environment. And here's where it gets stranger. The emissions from 3IATLAS don't behave like those from ordinary cometary ices. They're on-off, almost switch-like. When sunlight increases slightly, nickel emissions spike. When sunlight fades, they vanish. This behavior is exactly what one would expect from a compound, with a razor-thin thermal stability, window, like nickel tetracarbonyl. And exactly what you would not expect from simple outgassing of water ice or from the slow heating of dust. Grains. Something on or within 3IATLAS is responding to sunlight with chemical precision, as if following a rulebook of engineered chemistry, not natural physics. Ordinary cometary volatiles, water ice, carbon dioxide, carbon monoxide, sublimate gradually as they warm. The vapor pressure rises smoothly with temperature. There is no sudden jump, no clean line between frozen and gas. Nature in this case prefers a gradient, but that is not what we see with 3IATLAS. The nickel emissions do not ramp up. They switch on. Then just as abruptly they switch off. This isn't the behavior of ice. It's the signature of a parent molecule with a sharp decomposition threshold, a compound that remains inert until it crosses a precise thermal boundary. Nickel tetracarbonyl fits that description perfectly. Nothing else comes close. And that raises a deeply unsettling question. If nickel tetracarbonyl is really there, where did it come from? It cannot form naturally on Earth. It requires temperatures between 50 and 60 degrees, a controlled atmosphere of carbon monoxide, and the presence of metallic nickel. Conditions we associate not with geology or biology, but with industrial chemistry. So how did such a compound end up on a comet that supposedly formed in another star system, billions of years ago, and has been drifting through interstellar space ever since? One answer is the comforting one. We might simply not know enough yet. Perhaps there are astrophysical environments where nickel tetracarbonyl can arise naturally. Cold, dense molecular clouds where carbon monoxide is abundant and metal grains drift through the dark. Or protoplanetary disks rich in exotic chemistry near newborn stars. We've never directly detected nickel tetracarbonyl in interstellar space, but that doesn't mean it isn't there. Our molecular surveys are incomplete. The universe's chemical catalog is far from finished. If this compound can indeed form naturally, then 3IATLAS offers us a first glimpse of a chemistry alien to our solar system. A chemistry that evolved under different pressures, temperatures, and elemental ratios. That possibility alone would be revolutionary. It would mean that not all comets are built alike. That planet formation across the galaxy produces materials and reactions that defy our local experience. 3IATLAS in that case would not just be interstellar. It would be chemically interstellar, a messenger from a different kind of chemistry altogether. But there is another possibility, and it is the one that makes scientists uneasy. What if nickel tetracarbonyl on 3IATLAS is not the product of natural formation? What if it is deliberate? Nickel tetracarbonyl is a refining agent, used to produce high-purity metal. It is part of a manufacturing process, not a geological one. So imagine for a moment that 3IATLAS is not just a rock and ice conglomerate, but something constructed. Or at least something that once interacted with technology. If you were designing an object meant to endure the brutal emptiness of interstellar space for billions of years, you would need materials that are strong yet light, resistant to radiation, corrosion, and extreme temperature swings. Metals are tough but dense. Organics are light but fragile. Ice is common but ephemeral. It sublimates away. And yet, a thin nickel coating refined through carbonyl chemistry. That would last. The chemistry that shouldn't exist. Inside the 3IATLAS anomaly. Ideally, any long-duration probe, artificial or natural, would need a way to repair itself. A system capable of regenerating its surface as material erodes away. And that's where the idea turns strange. One compound fits the data better than anything else. Nickel tetracarbonyl. Toxic to humans, yes, but chemically fascinating. It can be synthesized from just two simple ingredients, nickel and carbon monoxide. Both are abundant in interstellar space. In principle, a sufficiently advanced system could harvest carbon monoxide from the interstellar medium and use it to rebuild a nickel-based surface, coating itself in a thin, protective layer that continuously regenerates as it wears away. It's speculative, but it's exactly the kind of chemistry you'd expect from an engineered probe built to last millennia. Then there's the post, an anonymous thread on 4chan's paranormal board. The user claimed that the dust from 3IATLAS was manufactured material, black, porous as smoke, made of large, complex particles unlike any natural ice or silicate grain. If that description is even partly accurate, and if the nickel emission we're seeing corresponds to a compound only known from industrial synthesis, then a pattern begins to emerge. A pattern that suggests the chemistry of 3IATLAS is not accidental. To be clear, this is not proof. It's inference, based on limited data, uncertain assumptions, and a chain of reasoning that could collapse under better evidence. But right now it fits, and when multiple independent observations all point in the same direction, you have to pay attention. Now let's move to the other chemical anomaly, the CO2 to H2O ratio, 87% to 4%. Not as dramatic as the nickel-iron issue, but still profoundly odd. Most comets are water-dominated. Carbon dioxide is a minor player. That's because of formation temperature. Water ice condenses closer to the star where it's warmer. Carbon dioxide ice forms farther out, in the deep cold of the outer disk. So a comet with this ratio, CO2 outweighing water by more than 20 to 1, doesn't match the chemical fingerprint of any known population. It hints at an origin zone we've never sampled, or a process we don't yet understand. 3IATLAS and the carbon dioxide paradox EF. 3IATLAS is truly carbon dioxide rich. Then it must have formed far from its parent star, in a realm colder than even the outer Kuiper belt of our own solar system. That's possible. Some stellar systems have extended protoplanetary disks, and others host giant planets that scatter icy planetesimals into the deep dark. A CO2-dominated comet is unusual, yes, but not impossible. Here's the catch. If 3IATLAS formed so far out that carbon dioxide became its dominant volatile, then it should be ancient and pristine, untouched by significant heating, because once a comet warms above a certain threshold, CO2 is the first thing to vanish. Its sublimation temperature is far lower than water's. Heat a comet enough to drive off the carbon dioxide, and the water follows. So a body that's still 87% CO2 can't have been warmed before. Not much anyway. And yet 3IATLAS is boiling off material at 150 kilograms per second. That's an enormous rate, too high for something supposedly unaltered since formation. If it has never been heated, why is it so active now? If it has been heated before, how does it still hold so much carbon dioxide? One possible answer is mass. If the object truly weighs in at tens of billions of tons, it could hide a vast internal reservoir of volatiles. Even if it lost surface material during earlier passes near other stars, its deep interior could remain cold, dense, and CO2-rich. As the outer layers sublimate, fresh volatile-laden strata are exposed, keeping the outgassing steady. It's plausible, but only barely. It demands a comet at the upper extreme of current size estimates, with an interior somehow preserved in cryogenic stillness, while its surface cooks in sunlight. It fits the math, but only just. And then comes the alternative, the one that unsettles every conventional model. What if the carbon dioxide isn't sublimating from ancient ice at all? What if it's being created? Through chemical reactions deep inside the body, the decomposition of carbonates, the release from clathrate hydrates, or something far stranger. Some have suggested an internal energy source, a decaying remnant perhaps from an earlier epoch of the universe itself. In that scenario, 3IATLAS would not be a passive relic, but an active engine processing carbon, oxygen, and nitrogen under its own internal radiation. In that case, what we're witnessing isn't sublimation, it's alchemy. The chemical factory hypothesis. Imagine a comet that doesn't merely sublimate but reacts. If 3IATLAS harbors an internal energy source, its core could act as a low-temperature chemical factory, quietly processing raw elements into complex molecules. In that scenario, carbon dioxide, carbon monoxide, cyanide, and other small molecules aren't relics of ancient ice. They're byproducts, the steady exhaust of decay-driven chemistry. The ratio of these molecules would no longer trace the conditions of formation, but rather the mechanics of the reaction itself. And that chemistry could easily favor carbon dioxide over water. Speculative? Yes, but disturbingly consistent with the data. Then there's the cyanide to nickel anomaly. In ordinary comets, cyanide, whether as hydrogen cyanide, HCN, or cyanogen, CN2, is common. It forms through reactions between carbon and nitrogen-bearing volatiles, a natural signature of primordial chemistry. Every comet we've ever observed carries some. The relative abundance, the cyanide ratio, offers clues to the temperature and chemistry of the comet's birthplace. But 3IATLAS breaks that rule. Its cyanide to nickel ratio isn't just unusual. It's off by orders of magnitude compared to any known comet, including 2I Borisov, the only other interstellar visitor we've studied in depth. Borisov's chemistry was different from solar system norms, but still within reason. A foreign accent, not a new language. IATLAS speaks something else entirely. Its nickel abundance is far too high relative to its cyanide. If both species were released by simple sublimation, gases venting from ancient ices, their ratio should remain close to the original composition, nudged only slightly by differences in volatility or photodissociation rates. Those effects are small, subtle. They don't shift numbers by orders of magnitude. Something else is at work. Something controlling the chemistry, not merely preserving it. The engineering hypothesis to create a deviation that large, the kind seen in 3IATLAS's cyanide to nickel ratio, you need one of two things. Either a bizarrely exotic initial composition, or a completely different source for one of the molecules. And here, again, nickel tetracarbonyl fits disturbingly well. If nickel is being released from the decomposition of a volatile compound, like nickel tetracarbonyl, while cyanide comes from the sublimation of refractory organics, Then the observed ratio reflects the balance between two very different chemical reservoirs. If the object happens to be enriched in nickel tetracarbonyl, for whatever reason, natural or artificial, the ratio tilts dramatically, exactly as observed. Then there's the dust. The polarization of light from 3IATLAS's dust is extreme, 2.7%, an unprecedented negative value. The only way to produce polarization that strong is if the dust particles have highly specific optical properties. They must be large, complex, and extraordinarily porous. Think fractal aggregates, tiny grains sticking together in clusters, then clusters of clusters building into vast, delicate frameworks, snowflakes made of soot and tar. Nature can do this. In a comet's coma, microscopic dust grains collide and cling through electrostatic forces, forming hierarchical fractal structures, porous, fluffy, mostly empty space. Such structures can indeed yield negative polarization, but the degree seen in 3IATLAS is beyond the edge of current models. Even the most generous simulations strain to reproduce it, and when you place that alongside the anonymous description from the 4chan leak, black and porous as smoke, manufactured material, the pattern starts to blur the line between natural aggregation and structural engineering. Could the dust be a designed material? Something like a nano-porous foam, or even an aerogel optimized for thermal insulation or radiation shielding. It's not necessary to invoke design. The polarization can be explained naturally, if you're willing to stretch the physics and tune every variable just right. But when every anomaly, chemical and physical, requires an edge case explanation, and all those edges point in the same direction, the coincidence begins to look deliberate. Let's add it up. Nickel without iron, implying nickel tetracarbonyl. Carbon dioxide dominating water, implying either cold, pristine formation or active internal chemistry. Cyanide to nickel ratio off by orders of magnitude, implying multiple distinct molecular sources. Dust polarization at record extremes, implying complex, possibly engineered structure. Each puzzle piece alone can be explained, barely, but all of them together, on the same object, start to defy statistical comfort. Occam's razor says the simplest explanation is usually correct. If 3IATLAS is natural, you need to assume a cold outer disk origin, exotic nucleosynthesis, improbable nickel chemistry, unconventional dust aggregation, and perfect orbital alignment, all at once. If it's not natural, you need only one assumption: it was made. From there, everything else follows. The chemistry, the trajectory, the composition, the precision, all deliberate, all engineered, but that single assumption carries weight. It requires admitting that we might not be observing geology or chemistry, but technology, and that is not a conclusion anyone reaches lightly. When physics gets weird, the burden of proof for an extraordinary claim is, as it should be, extraordinarily high. We need more data. We need to confirm the nickel tetracarbonyl hypothesis with higher resolution spectra. We need to test whether the dust polarization truly fits natural aggregate models, or whether it demands something more. We need to observe the coma in December and see if the predicted debris cloud appears. Until then, the chemistry remains a puzzle that whispers of something strange, but does not yet shout it. A puzzle that keeps pulling us back to the same uncomfortable question. If this is natural, why is it so perfectly weird? And if it isn't, what is it? When physics gets weird, the line between the natural and the impossible begins to blur. So what if 3IATLAS isn't a comet at all? What if it isn't even made of ordinary matter? What if the core of this object is a relic from the first microseconds after the Big Bang? A stable knot of exotic fields that has drifted through the galaxy for billions of years, invisible and inert, until the sun's gravity pulled it close enough to wake. This is the cue ball hypothesis. And as implausible as it sounds, it's not science fiction. It's theoretical physics, speculative, yes, but mathematically consistent with known laws, and predicted by certain extensions of the standard model of particle physics. Let's unpack that. In the very early universe, fractions of a second after the Big Bang, temperatures were so high that the four fundamental forces we know today, gravity, electromagnetism, the strong nuclear and weak nuclear forces, were unified into a single interaction. As the cosmos expanded and cooled, this unity fractured in a process called symmetry breaking. When a symmetry breaks, fields can become trapped in temporary metastable states, pockets of higher energy surrounded by barriers. Picture a ball resting in a shallow valley on a hillside, not at the lowest possible point but stuck in a local minimum. It's stable, unless something pushes it over the ridge. Now, in certain supersymmetric theories, extensions of the standard model that pair each known particle with a hypothetical partner, the mathematics allows for scalar fields that can form stable lumps of energy called solitons. A soliton is a self-contained knot of a field, a wave that does not disperse, held together by the precise balance of forces that try to expand and compress it. There are two main kinds: topological solitons, whose stability comes from the shape or topology of the field itself, and non-topological solitons or cue balls, whose stability comes from a conserved quantum charge. Imagine a field that carries a special charge, not electrical, but associated with a deeper symmetry. If a region of that field condenses into a coherent lump, all oscillating in phase, rotating in field space, the total charge cannot be broken apart without violating conservation laws. The result is a stable, self-contained object, behaving more like a macroscopic particle than a cloud of quanta. It has mass, size, and gravitational influence, but interacts only weakly with normal matter. If such things exist, they would have formed in the earliest instance of the universe, when high-energy fields were collapsing into their lowest states, and some regions got stuck. Most of the field energy decayed away into ordinary particles, but a few coherent lumps, cue balls, could have survived. They would drift silently through galaxies, invisible except through gravity, until something, say, a close pass by a star, triggered the outer layers to react, glow, and shed material. In other words, 3IATLAS might not be a comet imitating technology. It could be physics older than stars, imitating life. The cue ball hypothesis, Part 2. The dark heart of matter. Not every lump of primordial field energy would have decayed away. Those with a large conserved charge would have survived, dense ancient relics of the early universe. Their mass would be concentrated in volumes far smaller than any normal object of comparable weight. They would be astonishingly long-lived, their decay time stretching beyond the current age of the cosmos itself. That makes cue balls compelling dark matter candidates. We know dark matter exists, not because we can see it, but because we can't explain the universe without it. Galaxies spin faster than they should, held together by an unseen hand. Clusters of galaxies stay bound despite not having enough visible mass. Gravitational lensing bends light through invisible wells of gravity. Something is there, something massive, silent, and dark. For decades, physicists have hunted for WIMPs, weakly interacting massive particles, hypothetical building blocks of dark matter that would interact only through gravity and the weak nuclear force. But decades of searches have turned up nothing. No signal in detectors buried deep underground. No trace in particle accelerators. The WIMP paradigm isn't dead but it's gasping, and into that vacuum steps the cue ball. If dark matter is made of cue balls, it wouldn't be composed of invisible particles, but of macroscopic objects, each one a droplet of exotic field energy. Their masses could range from grams to kilograms, even higher depending on the theory's parameters. They would glide through ordinary matter almost untouched, ghost-like, because they interact so weakly. Most would pass unnoticed, but occasionally one might be captured by a planet, a star, or drift into the solar system. Now imagine one that has wandered the galaxy for billions of years, sweeping up interstellar dust and ice, forming a thin mantle of ordinary matter. As it nears the sun, that coating begins to sublimate, just like a comet's. Jets of vapor burst out, reflecting sunlight, creating a tail. But the core beneath and the true heart of the object is not ice, not rock, not metal. It's exotic matter, a relic of creation itself. That is the 3IATLAS cue ball scenario described in the post that reignited this mystery. A cue ball with a mass of tens of billions of tons, wrapped in a crust of ancient ice and dust accumulated across eons. Its core is inert, stable, and nearly invisible, but not entirely dead. Deep inside, the field is still slowly decaying, leaking energy into ordinary particles at a steady rate of roughly 73 megawatts. A faint heartbeat of power, negligible compared to its total mass energy, but enough to keep its mantle warm. Over cosmic timescales, that warmth drives chemistry. It cracks complex molecules apart, producing carbon dioxide, carbon monoxide, small hydrocarbons, all the familiar compounds we see in comets. But it also forges metals. As the exotic field decays, some of its energy becomes quarks and gluons, which bind into protons and neutrons. Over immense spans of time, low-energy nuclear reactions slowly fuse these into heavier elements. Not the explosive fusion of stars, but a quiet, patient transmutation, unfolding atom by atom. The result? Anomalous chemical ratios, nickel without iron, carbon-rich compounds in unusual proportions, fingerprints of a process unlike anything seen in natural comets. The test of the impossible, predictions and consequences. This is, of course, speculative. We do not know how cue-ball decay truly works, because we do not yet have a confirmed theory of supersymmetry. But the idea itself is sound, an internal energy source, operating quietly at cryogenic temperatures for billions of years, could sustain chemistry and produce a steady exhaust. And that exhaust may be what we are seeing. The power of the cue-ball hypothesis lies in its parsimony. It explains everything: the mass, the outgassing without recoil, the thermal stability, the bizarre chemistry, the improbable trajectory. If cue-balls are a component of dark matter, and if they exist in sufficient abundance to make up even a modest fraction of the galaxy's invisible mass, then the Milky Way is filled with them. Billions, perhaps trillions adrift in the dark. Most would be too small, too faint, or moving too fast to detect. But occasionally one passes close enough to a star for its outer mantle to awaken. Glowing, venting, masquerading as a comet. We may have found one not because we were lucky, but because they are everywhere. That makes the discovery of 3IATLAS not improbable, but inevitable. The Vera Rubin Observatory was barely operational when it spotted it, exactly what the cue-ball scenario predicts. If these objects are real, once our sky surveys reach full sensitivity, we should find them regularly, one every few months, spanning a spectrum of masses from tiny Oumuamua-like fragments to giants like 3IATLAS. A prediction you can test, and the hypothesis is testable. Watch the object as it retreats from the sun. If 3IATLAS is a normal comet, its activity should fade as it cools. By the time it crosses Jupiter's orbit, the jets should die down, the coma collapse, the light curve flatten. But if it is a cue-ball, the brightness will not fade. Its internal engine doesn't care about solar distance. It runs autonomously, powered by the slow decay of its field energy. If the activity remains steady deep into the outer solar system, we will know something extraordinary is happening. That's the first prediction. We will have our answer by mid-2026, the gamma-ray signature. The second prediction is even bolder: a gamma-ray signal. If the core truly releases 73 megawatts of power, that energy must emerge somehow. Most of it will dissipate as neutrinos, nearly impossible to detect. Some will appear as charged particles, heating the surrounding mantle, but a fraction should escape directly as gamma rays, high-energy photons born in the decay process itself. 73 megawatts is not much by human standards, less than a single large wind turbine. But when concentrated within the minuscule core of a cue-ball, the power density is immense. That should produce a faint, steady gamma-ray flux, non-thermal, non-solar, and non-random. In principle, telescopes like Fermi or NuSTAR could detect it. In practice, the challenge is formidable. The gamma-ray background is noisy. The sun itself emits gamma rays, as do cosmic rays striking interplanetary dust. 3IATLAS is a faint source moving against a bright, turbulent backdrop. But with the right energy window and enough integration time, the signal could stand out. A steady, persistent emission that does not vary with sunlight or distance. That would be the smoking gun. The stakes, as far as anyone knows. No gamma-ray telescope has been pointed at 3IATLAS yet, perhaps because the idea is too implausible. Perhaps because telescope time is precious and no one wants to gamble it on a ghost. But if the cue-ball hypothesis is even remotely possible, someone should look. Because if the signal is there, if the decay glow of exotic matter is caught on record, it will change everything. This would not just be the discovery of a strange comet. It would be the discovery of what dark matter truly is. It would mean that dark matter is not a sea of invisible particles, but a population of macroscopic structured entities, relics of the universe's infancy, drifting through the galaxy like silent, massive snowflakes of exotic field energy. It would mean that the cosmos is teeming with them, passing through solar systems, through planets, through us all the time, unseen and unsuspected. It would mean that dark matter can interact with ordinary matter, however faintly, forming mantles of dust and ice, scattering sunlight masquerading as comets. And if that is true, then some of the asteroids and comets we have catalogued for decades may not be what we think. They may be dark matter relics in disguise, ancient visitors from the first second of time, drifting through our skies, waiting for someone to notice. The Trojan horse in the sky, and that raises a chilling question. What happens if a cue ball hits Earth? 33 billion tons of exotic matter, moving at 60 kilometers per second. The kinetic energy works out to roughly 10,022 joules, about 50,000 megatons, or 5 million Hiroshima bombs. An impact like that wouldn't leave a crater. It would erase the landscape, vaporizing everything within hundreds of kilometers, igniting global wildfires, lofting megatons of dust into the stratosphere, and plunging the planet into a decade-long winter. An extinction-level event. Instant, absolute, and, for now, undetectable. The only consolation is statistical. Even if cue balls are common, the Earth's cross-section is infinitesimal compared to the volume of interstellar space. The odds of a direct hit in any given year are vanishingly small. But stretch the clock, over millions of years, over the full span of geological time, and that probability becomes uncomfortably real. And maybe, just maybe, it has happened before. Some extinction events in the fossil record remain unexplained. No crater, no asteroid, just a sudden pulse of heat, dust, and darkness. A cue ball strike would fit that pattern perfectly. A catastrophic energy release without a visible impactor, leaving only a chemical and biological scar. It is speculation, yes, but it is speculation worth taking seriously, because if cue balls exist, they represent a threat we are not prepared for. Our planetary defense systems are built to detect and deflect rock and metal, bright sunlit bodies that reflect visible light. A cue ball, wrapped in a thin mantle of dark ice and carbon dust, would be nearly invisible, fast, cold, silent. By the time our telescopes saw it, it might already be too close. The test that changes everything, all of this, of course, rests on a single assumption, that the cue ball hypothesis is correct. Right now, it is only that. An elegant theory that ties a dozen strange observations into one coherent story. It has not been proven. It has not even been tested, but we can test it. We have predictions, specific, measurable, falsifiable. Point a gamma-ray telescope at 3IATLAS. Track its activity as it drifts into the outer solar system. Measure the coma in December to see whether the debris cloud exists. Gather the data. Run the experiments. Let the results speak for themselves. If the cue ball idea fails, fine. Science advances as much by elimination as by discovery. But if it holds, if the gamma rays are real, if the outgassing does not fade, if the debris cloud never forms, then we are standing on the edge of something profound, a beautiful, terrifying problem. A revelation that dark matter is not what we thought, that the universe is stranger and more dangerous than we ever imagined. The Trojan horse of the cosmos, because if 3IATLAS is a cue ball, then the galaxy is not just a quiet sea of dust and stars. It is alive with massive, ancient things, silent engines from the dawn of creation, wandering between suns, sometimes brushing close enough for their mantles to catch fire and betray their presence. They look harmless. They look familiar. They look like comets, until you check the details and realize they are not comets at all. That is what the cue ball hypothesis gives us. Not certainty, but coherence. A single thread that ties every anomaly of 3IATLAS into a unified story. A story that, if true, will rewrite cosmology, and if false, will still be worth telling, because it shows how science works. You see something strange. You imagine the impossible. You test it, and you move forward, toward truth, or toward a sharper mystery. IATLAS is either the strangest comet ever observed, or the first direct glimpse of dark matter itself. By this time next year, we'll know. Until then, the cue ball hypothesis stays on the table. Improbable, perhaps, but not impossible. And in science, not impossible is all you need to justify taking a closer look. After all, Troy fell not because of its enemies, but because it mistook a gift from the unknown for something safe. The arrival direction is also interesting. 3IATLAS came from near the solar apex, the direction in which the sun itself is moving through the local interstellar medium. Statistically, this is not where you expect random interstellar debris to come from. Objects on random trajectories should arrive isotropically, from all directions. But both 1I Oumuamua and 2I Borisov came from roughly similar apex-adjacent directions, and now 3IATLAS joins that list. 3 points make a line, or at least the hint of a pattern. If these objects were launched from a fixed reference frame in the galaxy, say, from a population or civilization that tracks local stellar motion, the apex direction is exactly where you would send your probes if you wanted to intercept target stars efficiently. Third, the rotation. Observations of 3IATLAS's light curve show a complex, non-sinusoidal pattern, not the clean, periodic variation expected from a tumbling rock or comet nucleus. It suggests either a precessing body with a variable thrust component, or multiple reflective surfaces changing orientation independently. In spacecraft terms, that could mean attitude control, solar panels, radiators, or articulated instruments adjusting to maintain orientation relative to the sun. Again, not proof, but consistent. Fourth, the emissions. Spectroscopic data from the Canary Islands and from Mauna Kea have shown transient emission lines not easily explained by ordinary cometary volatiles. Nickel and iron vapor, and yes, but also hints of compounds that would require high internal temperatures or catalytic surfaces to form. A natural explanation is difficult. A technological one remains speculative but not impossible. If an onboard reactor or power source is venting trace byproducts, that could look very much like weird comet chemistry. The artificial hypothesis does not claim alien intent. It only posits engineering, that 3IATLAS could be an artifact of a technological process, ancient or modern, local or extragalactic. Think of Voyager or Pioneer after millions of years drifting between stars. Their trajectories, coatings, and outgassing signatures would look nothing like ordinary rocks either. Evobe's Trojan horse analogy is not about invasion, it's about epistemology. How do you tell a natural object from an engineered one when your only data come from telescopes millions of kilometers away? You look for patterns that defy randomness, synchronized acceleration, energy use decoupled from solar input, consistent signal timing, and material signatures inconsistent with known chemistry. Right now, 3IATLAS sits on the knife edge between the plausible and the extraordinary. The data are incomplete, the models uncertain, and the bias is strong. Scientists prefer dust to design, randomness to intention. But the universe does not care what we find comfortable. If the anomalous acceleration continues beyond the range where solar heating can drive it, if compositional analysis reveals refractory metals in ordered ratios, if any repeating radio or optical modulation appears, even once, then the Trojan horse hypothesis will have to be taken seriously. Until then, it remains what every good scientific idea should be: falsifiable, specific, and a little unsettling. Traced back through the galaxy, 3IATLAS comes from a region within 9 degrees of the WOW signal. The WOW signal was a strong narrowband radio transmission detected in 1977 that has never been explained. Most likely it was terrestrial interference or a transient astrophysical event. But the coincidence is there. If you wanted to design a mission that arrives at a star system from a specific direction, you could. Interstellar trajectories are deterministic. Aim carefully when you launch and you arrive where you intended billions of years later. Third, the appearance. If you were designing an interstellar probe, what would it look like? Metal and electronics are fragile. Radiation damage, micrometeorite impacts, thermal cycling. Over millions of years, even the most robust materials degrade. A better design is to coat the probe in ice. Use the interstellar medium as a construction material. As the probe travels, it sweeps up hydrogen, water, carbon dioxide, dust, all the stuff floating in space. This accretes onto the surface. Over time, you build up a thick protective shell. When the probe approaches a star, that shell starts to sublimate. It looks exactly like a comet. This is not a new idea. It was proposed in the 1960s by researchers thinking about how to build long-duration interstellar missions. You do not carry all your shielding with you. You grow it en route, and when you arrive, the shielding doubles as camouflage. A probe coated in ice looks natural. It blends in. It does not trigger alarms. By the time anyone realizes it is not a normal comet, it is already in the system close to the planets gathering data. 3IATLAS fits this profile. It has a coma. It is outgassing. It has the spectral signatures of a comet. But underneath there are anomalies. The mass is too high. The chemistry is wrong. The behavior is too controlled. It is as if the outer shell is real, but the core is something else. Fourth, the energy budget. 3IATLAS is absorbing gigawatt of solar power. At perihelion with 770 WP square meter of sunlight, an object 5 km across intercepts roughly $15 That energy has to go somewhere. For a normal comet, it goes into heating the surface, sublimating ice and radiating back into space as infrared. The surface heats up until the outgoing radiation balances the incoming sunlight. But 3IATLAS is cold. The thermal observations show a surface temperature much lower than expected for an object at that distance from the sun. It is as if the energy is being absorbed but not radiated. Where is it going? If the object has an internal structure, a core with high thermal conductivity or some kind of active cooling system, it could transport the energy inward and store it or use it. This is speculation, but it's the kind of thing you would expect from a machine. Efficient thermal management, no waste heat signature, just enough sublimation from the surfaces to maintain the comet disguise. Fifth, the nickel. If you were building a probe and you needed structural materials, what would you use? Steel is an obvious choice. Strong, durable, easy to work with. But steel is mostly iron. If your probe is coated in ice and Thetis is sublimating, you would expect to see iron vapor in the coma, unless you're using a different alloy, nickel steel, or pure nickel. Nickel is stronger than iron for the same weight. It is more resistant to corrosion, and it can be refined to extreme purity using nickel tetracarbonyl, which is volatile and easy to handle if you have the right equipment. If 3IATLAS is artificial, and if its internal structure is made of nickel alloys, then as the surface erodes you would see nickel being released, not from sublimation of ice, from ablation of metal. The nickel tetracarbonyl could be a byproduct of that process, the metal reacting with carbon monoxide in the coma, forming the compound, then breaking down again under sunlight. This would explain why the nickel emission is so strong and why it is not accompanied by iron. Again, speculative, but consistent. Sixth, the silence. If 3IATLAS is a probe, it is not transmitting, at least not in any way we have detected. SETI organizations have pointed radio telescopes at it. Nothing. No signals in the obvious frequency ranges, no patterns in the visible light, no laser pulses. If there is a probe inside, it is either passive, just observing and recording, or it is using a communication method we do not recognize. Or maybe it is not trying to communicate with us at all. Maybe it is communicating with something else, another probe, a mothership farther out in the solar system, a base on a distant moon. Or maybe it is just gathering data and will transmit it later, once it is far enough away that we cannot intercept the signal. The lack of obvious signals is not evidence against the artificial hypothesis. It is expected a well-designed probe would not announce itself. It would operate quietly, blend, complete its mission, and leave. Only if we look very closely at the details do we start to notice the inconsistencies. And by the time we notice, it is too late to do anything about it. Now let us talk about intent. If 3IATLAS is a probe, what is it doing? The optimistic answer is that it is just exploring, gathering data, mapping the solar system, taking pictures, measuring magnetic fields, radiation levels, planetary atmospheres. This is what our probes do when we send them to other planets. Curiosity, science, understanding. If there is another technological civilization out there, and if they have the capability to send probes across interstellar distances, they might be doing the same thing we are exploring, learning, looking for life. This is the benign scenario, and if it is true, then 3IATLAS is not a threat. It is an opportunity, a chance to learn about another civilization, to see what they consider important, to understand their technology, maybe even to find a way to communicate. But there is a darker possibility. The dark forest hypothesis. This is a solution to the Fermi paradox, the question of why we have not seen evidence of extraterrestrial civilizations despite the galaxy being old enough for them to have arisen many times over. The dark forest hypothesis says that civilizations stay silent because the galaxy is dangerous. Broadcasting your presence is suicide, because if another civilization detects you and if they are more advanced, they might decide you are a threat and eliminate you preemptively. In this scenario, the galaxy is full of civilizations, but they are all hiding, staying quiet, observing, but not revealing themselves. And if you do reveal yourself, if you send signals or launch probes or make yourself visible, you risk attracting attention from someone who sees you as a competitor for sources. If 3IATLAS is a probe sent by a civilization that subscribes to the dark forest philosophy, then its purpose might not be benign. It might be reconnaissance assessing whether Earth is a threat, whether we have technology advanced enough to be dangerous, whether we should be left alone or neutralized. This is the paranoid scenario, and it is important to note that there is no evidence for it. The dark forest hypothesis is fiction, a thought experiment. There is no reason to think it describes the real galaxy, but it is a scenario that has been considered by serious researchers thinking about the risks of contact with extraterrestrial intelligence. If 3IATLAS is artificial, and if it is part of a reconnaissance mission, then the fact that it passed during solar conjunction takes on a more sinister tone. It was not just avoiding observation, it was minimizing the risk of detection while maximizing the information it could gather. It passed close to Mars, Venus, Jupiter. It came within observing distance of Earth, it mapped the system, and now it is leaving. What happens next depends on what it found. If we are deemed harmless, maybe nothing. If we're deemed a threat, maybe a follow-up mission, a larger probe, something designed not to observe but to act. This is speculation layered on speculation, but it is worth thinking through. Because if the artificial hypothesis is correct and if the intent is hostile, then we need to start thinking about planetary defense in a completely different way. Not defending against asteroids, defending against technology. The good news, if there is any, is that we have time. 3IATLAS is leaving. If it is a probe, it is not staying. It is not setting up a base on Mars. It is not parking in orbit around Earth. It is on a hyperbolic trajectory that will take it out of the solar system and back into interstellar space. By the end of 2026, it will be beyond Jupiter. By the end of the decade, it will be too faint to track. Whatever its mission was, it is sending, unless it released sub-probes. Small satellites left behind in strategic locations on the surface of Mars, in orbit around Venus, drifting near Earth, too small to see with telescopes, waiting, watching, transmitting data back to the mothership as it departs. This is the nightmare scenario, and there is no evidence for it. But if 3IATLAS is artificial, it is a possibility that cannot be ruled out without direct searches, and we are not doing those searches. We are not looking for small satellites in unusual orbits. We are not checking for anomalous radio transmissions from Mars. We are treating this as a comet, because that is what it looks like, and we are not considering. The Alternatives Low has been vocal about this. He argues that we should take the possibility of artificial origin seriously enough to mount a proper investigation. Not because it is likely, but because the consequences if we are wrong are severe. If this is a probe and if we ignore it, we miss a once-in-a-lifetime opportunity to study extraterrestrial technology. If this is a probe with hostile intent, and if we ignore it, we leave ourselves vulnerable. The Trojan horse fell because the defenders did not check inside. They assumed it was safe. They were wrong. Lowe is saying, check inside, use every tool we have. Gamma ray telescopes, radio dishes, high-resolution imaging, spectroscopy. Look for anything that does not fit the comet model, and if we find something, deal with it. Do not assume, verify. The problem is resources. Telescope time is expensive. Spacecraft missions take years to plan and billions of dollars to execute. Convincing funding agencies to spend money on what most people consider a low-probability scenario is difficult, especially when the object is leaving and the window of opportunity is closing. But this is exactly when you should spend the resources. When the stakes are high and the time is limited. If 3IATLAS is just a comet, we waste some telescope time and learn interesting things about cometary chemistry. If it is a probe, we potentially learn things that change human civilization forever. The risk-reward calculation is asymmetric. The cost of checking is small. The cost of not checking if we are wrong is enormous. So why are we not checking more aggressively? Part of it is institutional inertia. NASA and other space agencies have procedures, protocols, committees. Everything moves slowly. By the time a proposal to study 3IATLAS with dedicated resources works its way through the system, the object will be gone. Part of it is scientific conservatism. Most astronomers believe 3IATLAS is a comet with weird properties. Not a probe, not a cue ball, just a comet. And they might be right. But science advances by testing hypothesis, not by assuming the default answer is correct. If there is a credible alternative explanation that fits the data, it should be tested. And part of it is fear. Fear of being wrong. Fear of looking foolish. Fear of being the person who claimed to find alien technology and turned out to be mistaken. This fear is understandable. Careers are built on credibility. Reputations are fragile. No one wants to be the next person who cried alien and got laughed out of the field. But this fear is also corrosive. It prevents us from asking bold questions. It keeps us from exploring the edges of possibility. It makes us conservative when we should be curious. And in the case of 3IATLAS, it might be preventing us from seeing something extraordinary. The Trojan horse theory is not proven. It might never be proven, but it is unthinkable. And as long as it is unthinkable, we have a responsibility to check, to verify, to test. Because if we're wrong, and if we dismiss this as just another comet, we will never know what we missed. December 19th is coming. Closest approach to Earth. Best observation window. We will see if the debris cloud is there. We will see if the chemistry makes sense. We will see if the behavior matches a natural comet or if the anomalies persist. And maybe, just maybe, someone will point a gamma ray telescope at it and listen for the heartbeat of a machine. Until then, the Trojan horse sits outside our gates, familiar, harmless, a gift from the cosmos, and we have to decide whether to bring it inside or whether to be suspicious and check first. The defenders of Troy did not check. They paid the price. We have a chance to do better. The December 19th reckoning, December 19th, 2025. Mark it on your calendar. That is the day 3IATLAS makes its closest approach to Earth. 267 million kilometers, just over 1.7 astronomical units. Farther than the sun, but close enough. Close enough for hundreds of ground-based telescopes to observe it. Close enough for Hubble and James Webb to take high-resolution images and spectra. Close enough to settle once and for all whether the massive debris cloud that should be there is actually there. This is the test, the moment when speculation either becomes confirmation or evaporates into noise. Because if the cloud is there, if we see billions of tons of gas expanding outward from the nucleus, then 3IATLAS is a comet. Weird chemistry, yes. Unusual composition, yes, but fundamentally natural. The non-gravitational acceleration at perihelion was caused by outgassing. The anomalies are just their salt of formation in an exotic environment. Case closed. If the cloud is not there, everything changes. Let me explain what we are looking for. During October, 3IATLAS experienced a non-gravitational acceleration that corresponds to losing about 10 to 15% of its total mass. If the object is 33 billion tons, that is 3 to 5 billion tons of material ejected into space, that gas does not disappear. It expands outward at a few hundred meters, the thermal velocity of sublimated carbon dioxide and water. By December 19th, 2 months after perihelion, that gas will have traveled about 5 million kilometers from the nucleus. It will form a diffuse cloud, still centered on the object, but spread out over a huge volume. This cloud will be faint, very faint. The density is low and the gas is cold, so it does not emit much light, but it will scatter sunlight, and it will emit spectral lines from molecules like carbon dioxide, carbon monoxide, water, cyanide, all the volatiles we've been seeing in the coma. The total brightness of the cloud integrated over its entire extent should be measurable, not with the naked eye, not with amateur telescopes, but with professional instruments, Hubble, Webb, large ground-based observatories with sensitive spectrographs. If the cloud is there, we will see it. The signal-to-noise ratio will not be great, but it will be above the detection threshold. Multiple independent observations will confirm it, and the mass of gas in the cloud will match within uncertainties the amount required to explain the acceleration. If the cloud is not there, or if it is there but much smaller than predicted, then the outgassing explanation fails, and we are left with a puzzle. The object accelerated, but it did not eject enough mass to cause that acceleration through the rocket effect. So what did cause it? Internal propulsion. That is the obvious alternative. Some kind of engine or thruster that produces thrust, without ejecting large amounts of reaction mass. This could be a technology if 3IATLAS is artificial, or it could be a natural process we do not understand, if it is a cue ball or some other exotic object. Either way, the absence of a debris cloud would be strong evidence that 3IATLAS is not an ordinary comet. Now, there are a few caveats. The cloud might be there but difficult to detect. If the gas is very cold, or if it is optically thin, or if it has been dispersed by solar wind more than we expect, the brightness might be lower than predicted. This would make detection harder. We might see a faint signal that is marginally consistent with a small amount of outgassing, but not enough to fully explain the acceleration. In that case, the interpretation becomes ambiguous. Maybe there was some outgassing but also some other effect, or maybe our models of gas expansion and emission are wrong. Science is rarely clean. Real data is messy. Uncertainties are large. But there is a difference between a marginal detection and a null result. If we see nothing, or if we see something that is orders of magnitude smaller than expected, that is not ambiguous. That is a clear signal that the outgassing hypothesis is inadequate. So what happens on December 19th? A lot of telescopes will be pointed at 3IATLAS, professional observatories, space telescopes, amateur astronomers with good equipment. The object will be magnitude 14 or 15 depending on how its brightness has evolved since perihelion. That is faint but observable with medium to large telescopes in dark skies. The professional observations will focus on spectroscopy, measuring the exact composition of the coma and any extended emission around the nucleus, looking for carbon dioxide, carbon monoxide, water, cyanide, nickel, all the species we have been tracking, and crucially measuring the spatial distribution. How far from the nucleus does the emission extend? Is there an extended halo consistent with an expanding cloud? Or is the emission confined to a small region near the nucleus, consistent with ongoing low-level outgassing, but not with massive ejection? Hubble and Webb will take images in multiple filters, visible, infrared, ultraviolet. These images will show the morphology of the coma. Is it round, elongated, asymmetric? Are there jets or features? The resolution will be good enough to see structure on scales of a few thousand kilometer. Not good enough to resolve the nucleus directly, but good enough to characterize the immediate environment. Ground-based observatories with large mirrors and adaptive optics will do similar imaging. Some will use narrowband filters tuned to specific emission lines like the CNC cyanide line or the C2 carbon molecule line. This allows them to map the distribution of specific molecules, which can reveal details about the outgassing pattern. Radio telescopes might observe as well. ALMA. The Atacama Large Millimeter Array can measure carbon monoxide and other molecules at millim wavelengths. These observations are less affected by dust scattering and give a direct measure of the gas content. If there is a massive cloud of carbon monoxide, ALMA will see it. All of this data will come in over the course of several weeks around December 19th, not all at once. Different telescopes observe at different times. Data processing takes time. Results get shared among research groups. By early January, we should have a clear picture of what the coma looks like and whether the debris cloud is there, and then the papers start appearing. Preprints on Therif server. Submissions to journals, press releases if the findings are significant. The scientific community will debate the interpretation. If the cloud is there, some will say, see, it is just a comet, case closed. Others will say, but what about all the other anomalies, the chemistry, the trajectory, the mass? The debate will continue. But the artificial and exotic hypothesis will lose credibility. If the cloud is not there, the debate shifts. The comet hypothesis loses credibility. Alternative explanations move to the forefront. Low will say, I told you so. We need to consider non-natural origins. Mainstream astronomers will scramble to find natural processes that could explain the acceleration without massive outjing. Magnetic fields, radiation pressure on the nucleus, fragmentation events that we missed something, anything. Because the alternative, admitting that we are looking at technology or exotic physics, is uncomfortable. But discomfort is not a scientific argument. If the data does not support the comet hypothesis is wrong, and we move on to the alternatives. Uncomfortable or not, there is another prediction to test in December, the gamma-ray signature. If 3IATLAS is a cub, its core is decaying at a rate of 73 megawatt. This should produce a steady flux of high-energy photons, not a lot. The object is far away and the power output is small, compared to astrophysical sources like pulses or active galactic nuclei, but detectable if you know where to look, and you integrate long enough. As far as I know, no gamma-ray observatory has observed 3IATLAS yet. Fermi, the space-based gamma-ray telescope, has a limited field of view and is usually looking at other targets. NuSTAR, which observes in hard X-rays and soft gamma rays, could potentially detect a signal, but would need to be pointed directly at the object for an extended period. This requires a formal observing proposal, peer review, approval, and scheduling. All of that takes time. If someone does point a gamma-ray telescope at 3IATLAS in December, and if they detect a non-thermal signal that does not correlate with solar activity, that would be extraordinary. It would be the first direct evidence that the core is not ordinary matter. It would not prove the Kubel hypothesis conclusively, because there might be other explanations for a gamma-ray source, but it would make the hypothesis much more credible. If no gamma-ray signal is detected, that does not rule out the Cub hypothesis. The predicted flux might be below the detection threshold, or the emission might be at energies outside the range of available detectors. Absence of evidence is not evidence of absence, but a positive detection would be game-changing. Beyond December, there are other milestones. The International Asteroid Warning Network, IWN, has added 3IATLAS to its monitoring list. This is unusual. IWN typically tracks objects that pose a potential impact threat to Earth. 3IATLAS is on a hyperbolic trajectory. It is not going to hit Earth, but IWN is treating it as a training exercise for tracking unpredictable objects. The monitoring campaign runs from November 27, 2025 to January 27, 2026. Multiple observatories around the world will coordinate observations, sharing astrometric data to refine the orbit and track the non-gravitational acceleration over time. This campaign will provide the best astrometric data we have ever had for an interstellar object. High-precision measurements of position over 2 months. If the orbit shows any additional unexpected changes, any further accelerations or deviations, the data will catch it. This is important because it allows us to test whether the non-gravitational force is a constant or variable. A constant force suggests a steady outgassing rate or a steady internal engine. A variable force suggests something more complex. Jets turning on and off. Maneuvers, course corrections. If 3IATLAS is artificial, and if it is still under active control, it might maneuver again subtly. A small correction to ensure it passes specific locations at specific times, or a more dramatic change if it decides to alter its trajectory for some reason. The IWN campaign will detect it. ESA's JUICE spacecraft is scheduled to observe 3IATLAS in late November. JUICE is on its way to Jupiter, but it passed relatively close to the object's position in space and was able to point its instruments at it. The observations were done. The data is being transmitted back to Earth. But because JUICE is far from Earth and the data rate is slow, we will not see the results until February 2026. What will JUICE see? Probably similar to what the Mars orbiters saw. A fuzzy blob of light, a coma with some structure, maybe evidence for jets or asymmetry. The resolution will not be as good as HiRISE was supposed to be, but it will be better than ground-based observations. And because JUICE observed the object after perihelion, the data will show whether the activity has declined or stayed constant. If it has stayed constant, that supports the Cub hypothesis. If it has declined, that supports the comet hypothesis. March 2026 is when 3IATLAS passes Jupiter. The distance will be significant, not a close flyby, but close enough for Jupiter-based observatories to observe if any are looking. Ground-based telescopes on Earth will still be able to track it, though it will be fainter as it moves farther from the Sun. By this point, 5 months after perihelion, a normal comet should be much less active. The sublimation rate should have dropped. The coma should be smaller and dimmer. If 3IATLAS is still bright, still outgassing at the same rate, that is another data point against the comet hypothesis. By mid-2026, the object will be moving into the outer solar system beyond Jupiter's orbit. Fainter and fainter, harder and harder to observe. By the end of the year, it will be at the limit of what even large professional telescopes can detect. By 2027, it will be gone. Just another faint dot among the background stars, indistinguishable from distant galaxies and asteroids, unless you know exactly where to look. And that is it. Our window closes. If we have not figured out what 3IATLAS is by then, we probably never will. It will become a footnote in history. The third interstellar object, the one with weird chemistry and unexplained acceleration, the one that sparked a brief controversy and then faded into obscurity as people moved on to the next thing, unless the results from December are unambiguous. Unless the debris cloud is absent, unless the gamma-ray signal is detected, unless something happens that forces the scientific community to confront the fact that this object does not fit our models and cannot be explained away with minor tweaks. If that happens, 3IATLAS becomes more than a footnote. It becomes a paradigm shift. It becomes the object that taught us dark matter has structure, or the object that confirmed we are not alone, or the object that revealed a new class of astrophysical phenomena we had never considered. Whatever the answer turns out to be, if the answer is not boring comet with weird chemistry, then December 19, 2025 becomes a date we'll remember. The day we saw something that did not fit and the day we started asking better questions. 45 days from now as I record this on November 4th. 45 days until we know. Until the data comes in and the debate either ends or intensifies. 45 days until we find out if 3IATLAS is the most interesting comet ever discovered, or if it is something else entirely. The clock is ticking. Telescopes are being scheduled. Observing proposals are being written. Researchers are preparing their instruments and their analysis pipelines. And somewhere 267 million km from Earth, a small dark object is coasting through space, oblivious to the attention it is receiving, carrying with it the answers to questions we are only beginning to ask. December 19th, Mark your calendar. This is when we find out if the universe is stranger than we thought or if it is just strange in the ways we already understand. Either way, the data will be fascinating, and the story, whatever it turns out to be, is worth paying attention to. Because this is how science works. You see something unusual, you make predictions, you test them, and you let the universe tell you whether you are right. Sometimes the answer is boring, sometimes it is extraordinary, but you do not know until you look. And December 19th is when we look the galaxy that is swirling with them. We have found 3 interstellar objects, 3 in 8 years. Umama in 2017, Boris in 2019, 3IATLAS in 2025. 3 objects out of billions of years of astronomical observation. 3 visitors from beyond our solar system, each one stranger than the last. And if the statistics are right, this is not rare. This is normal. The galaxy is full of them. Let me walk you through the numbers. Before 2017, we had found 0 interstellar objects. We knew they had to exist. Stars eject material all the time. Planets get scattered by giant planets. Some of them reach escape velocity and wander into interstellar space. Billions of years of ejection from billions of stars means there should be a background population of free-floating objects drifting through the galaxy. Comets, asteroids, maybe planets ejected during the chaotic early phases of system formation. The question was not whether they exist, but how many and whether we could detect them. In 2017, we detected one Oumuamua discovered by the Pan-STARRS telescope in Hawaii. A small object maybe 100 memis across on a hyperbolic orbit. It came in fast, passed close to the sun and left. We had a few weeks to observe it before it faded from view. The data was sparse, but it was enough. Non-gravitational acceleration, extreme geometry, unusual color. It was weird, but more importantly, it was there. Proof that interstellar objects pass through the solar system and that we can detect them with modern survey telescopes. The discovery rate implications were immediate. If we found one object in a few years of surveying with Pan-STARRS, ATLAScope with a relatively small field of view and modest sensitivity, then the population must be large. Extrapolating from one detection, researchers estimated there are thousands of Oumuamua-sized objects passing through the solar system at any given time. Most of them too faint or too fast to detect, but enough that a dedicated survey would find them regularly. 2 years later, Boris discovered by amateur astronomer Gennady Boris using a homemade telescope, larger than Oumuamua, about 400 meters across, actively outgassing a proper comet, not an inert rock. The data was much better because we had more warning. Boris was detected farther from the sun, so we had months to observe it as it approached and then receded. Spectroscopy, imaging, polarization. It had weird chemistry. Carbon monoxide-ig, but it was recognizably a comet. Natural. Expected 2 objects in 8 years. Small and weird. Borisov, medium and less weird, and then 3IATLAS, large and extremely weird. The progression is striking. Each object is bigger than the last. Each object is stranger than the last, and we found them quickly. Not over decades or centuries, over 8 years. This is faster than predicted. The original estimates based on ejection models and the mass budget of planetary systems suggested we would find about 1 interstellar object per year. With a next-generation survey telescope like the Vera Rubin Observatory, Rubin went operational earlier this year. It has an 8.4 mirror and a 3.22 GPA camera. It images the entire visible sky every 3 nights down to magnitude 24.5. If something moves, Rubin sees it. The fact that we found 3 objects before Rubin even started full operations suggests the population is denser than expected, or the objects are brighter than expected, or both. Revised estimates taking into account the discovery rate so far suggest we might find 1 interstellar object every few months. Once Rubin is fully operational, maybe more. By the end of the decade, we could have dozens. By the end of the next decade, hundreds. This is transformative. It changes interstellar objects from rare curiosities to a routine class of astronomical phenomena. We will have a statistical sample. We can measure the size distribution, the composition distribution, the velocity distribution. We can compare objects from different regions of the galaxy and see if there are patterns. This is how you do science. 1 object is an anomaly. 10 objects is a dataset. 100 objects is a field of study. But here is where it gets strange. The 3 objects we have found so far do not follow the expected size distribution. Oumuamua is small. Borisov is medium. 3IATLAS is huge. If you plot size versus discovery order, you get an increasing trend. That is backwards. Small objects should be more common than large objects. In every population of debris we have ever studied, asteroids, Kuiper belt objects, comets, the size distribution follows a power law. Lots of small things, fewer big things. If you're sampling randomly, you should find small ones more often. But we found a big one in our third detection. Why, one possibility's luck, we got lucky. In a sample of 3, anything can happen. Statistical fluctuations. You flip a coin 3 times and get 3 heads. Unlikely but not impossible. If we keep observing and the next 10 objects are all small, the anomaly disappears. The size distribution averages out. 3IATLAS was just the tail of the distribution, the rare large object we happen to catch early. Another possibility is bias. Maybe large objects are easier to detect. They are brighter because they have more surface area, or they are more active because they retain heat longer. They have larger COM that scatter more sunlight. Detection bias could skew the sample toward large objects even if small ones are more common. This is plausible, but it does not explain why Oumuamua, the smallest, was the first we found. If large objects are easier to detect, why did not we find 3IATLAS before Oumuamua? A third possibility is that the size distribution is not what we thought. Maybe interstellar objects do not follow the same power law as solar system objects. Maybe the ejection process favors certain sizes. Or maybe there are multiple populations, small objects from one process, large objects from another. If 3IATLAS is a cub or an artificial probe, it is not part of the same population as Borisov. It is a different category entirely. And if there are multiple categories, the statistics change. This is where the 4chan post becomes relevant. The anonymous ESA researcher claimed that finding an object as massive as 3IATLAS this early means the galaxy is swarming with them. The models are wrong by a factor of 10,000. Our entire picture of what gets ejected from solar systems is fundamentally flawed, or this object is not debris at all. If 3IATLAS is a cue ball, and if cue balls are dark matter, then the population is enormous. Dark matter outweighs ordinary matter by a factor of 5. If even a small fraction of dark matter is in the form of macroscopic objects like cue balls, there are trillions of them in the galaxy. They pass through the solar system all the time. We just do not see them because they do not scatter light. They're invisible until they accrete a mantle of ice and pass close enough to aster for that ice to sublimate. The Cub hypothesis predicts a specific detection rate if the dark matter density near the sun is the standard value, about 0.3 electron volts per sum. And if Cub balls make up a significant fraction of that density, then the flux of Cub balls through the solar system is calculable. You take the density, divide by the typical mass, multiply by the velocity dispersion, and you get a number, objects per year passing within ascertained distance of the sun. The numbers depend on assumptions, but they are in the right ballpark. A few per year passing close enough to develop COM, maybe 1 per decade, massive enough to be easily detectable. Finding 3IATLAS in our third interstellar object detection would not be surprising. It would be expected. If this is right, then as Ruben continues surveying, we will find more. Not just comets, not just asteroids, cue balls, or at least objects with the properties of CQ balls. Large, dense, weird chemistry, constant activity even far from the sun, gamma ray emission, all the signatures. And if we find even one more object that fits the profile, the hypothesis becomes much stronger. But there is another implication. If Cubs are common, and if they are dark matter, then dark matter is not passive. It is not just invisible mass that sits there and makes galaxies rotate faster. It is active. It has structure. It interacts with normal matter in complex ways. This changes cosmology. It changes galaxy formation models. It changes everything we thought we understood about the universe. It also means we are in danger. Cue balls, if they are common, are an impact threat. A 33 billion ton object moving at 60 kilometers kinetic energy, equivalent to millions of nuclear bombs. An impact like that would be catastrophic. Global extinction event, and we would have no warning because we cannot see cue balls until they are already inside the solar system outgassing near the sun. By the time we detect them, there might be weeks or months before impact. Not enough time to mount a meaningful defense. This is not a comfortable thought. But if the CQ ball hypothesis is correct, it is a threat we need to take seriously. Our planetary defense systems are designed for asteroids. We track them years in advance. We have time to plan deflection missions. CQ balls do not give us that luxury. They come in dark and fast. We see them only when they light up. And if phone is on a collision course, we might not be able to stop it. The good news, if there is any, is that the cross-section is small. Earth is a tiny target. Space is big. Even if there are trillions of Cubs in the galaxy, The odds of one hitting Earth in any given century are low. But over geological timescales, over millions of years, the probability increases. And if Cub balls are responsible for some of the unexplained mass extinction events in Earth's history, then this is not just a theoretical concern. It is a real threat with a track record. Now let us talk about the artificial hypothesis. If 3IATLAS is a probe, what does that mean for the population of interstellar objects? If 1 in 100 interstellar objects is artificial, and if we are detecting objects at a rate of a few per year, then we should find another artificial object within a few decades. That is testable. We keep observing, we keep characterizing, and we see if the anomalies cluster or if they are spread out. If anomalies are rare, if 3IATLAS is the only weird one and everything else is mundane, then the artificial hypothesis loses credibility. One anomaly can be explained as a statistical fluke or a natural object with extreme properties. 10 anomalies, all pointing toward technology, is harder to dismiss. But there is another possibility. What if artificial probes are common? What if every advanced civilization sends probes to explore nearby star systems? The galaxy is 10 billion years old. There has been plenty of time for civilizations to arise, develop technology, and launch exploration missions. If probes are long-lived, if they can operate for millions or billions of years, then the galaxy could be full of them. Ancient artifacts drifting, observing, waiting. This is the Bracewell probe hypothesis, named after radio astronomer Ronald Bracewell, who proposed in the 1960s that the most efficient way to explore the galaxy is not to send signals, but to send probes. A probe can travel slowly, taking thousands or millions of years to reach a target system. But once it is there, it can observe directly. It can send back detailed data. It can respond to local conditions. And if it is designed to be self-replicating, one probe can spawn many, exponentially increasing the coverage. If Bracewell probes exist, and if they have been seeded throughout the galaxy over billions of years, then theist density could be significant. Not one probe per star system, but maybe one probe per 100 star systems, or one per 1,000. Enough that a few should pass through our solar system per century, most of them silent, inactive, just drifting. But some might still be operational, still observing, still transmitting. 3IATLAS could be one of these. An ancient probe billions of years old, launched by a civilization that might not even exist anymore, coated in ice, passing through the solar system on a routine survey, gathering data and then leaving its mission complete, heading back into the void. If this is true, if Bracewell probes are real and common, then we are living in a galaxy that is far more connected than we thought. Not through radio signals, through physical artifacts, messengers, explorers, each one carrying information about its creators and its journey. And if we can find them, if we can study them, we can learn things about the galaxy that no telescope or particle detector could ever tell us. But this is all speculation. We have 3 data points, not enough to draw firm conclusions. We need more, and Ruben will give us more. By 2030, we will have a much better sense of the interstellar object population. We will know the size distribution, the composition distribution, the velocity distribution. We will know if 3IATLAS is an outlier or if it is part of a pattern. And if it is part of a pattern, if we find more objects with similar properties, large, dense, weird chemistry, anomalous behavior, then the conversation shifts. We stop debating whether 3IATLAS is weird and start asking what the weirdness means. We stop treating interstellar objects as rare curiosities and start treating them as a new class of phenomena that we need to understand. This is the promise of the next decade. The Vera Rubin Observatory, the next generation of surveys, the systematic study of interstellar objects. We're on the cusp of turning a trickle of data into a flood. And floods reveal patterns. They reveal structures. They reveal truth that individual droplets cannot show. 3. Atlas is a droplet, a single object. Strange, provocative, but isolated. The question is whether it is the first of many or the only one of its kind. And we will not know the answer until we find more. So we watch, we wait, we survey, and we see what the galaxy sends us next. Because if 3IATLAS has taught us anything, it is that the universe is full of surprises. Some of them small, some of them large, and some of them so strange that they make us question everything we thought we knew. What comes next? We stand at a crossroads. In one direction, 3IATLAS is a comet. Strange, yes. Chemically unusual, absolutely, but fundamentally natural. A relic from another star system with properties that push the boundaries of what we understand about cometry formation, but nothing that breaks physics. In this direction, science proceeds. Normally, papers get published, models get refined, the anomalies get explained one by one with clever ideas about exotic formation environments and rare chemical processes. Life goes on. In the other direction, 3IATLAS is something else. A cue ball, a probe, a dark matter relic, or an artificial construction. In this direction, everything changes. Our understanding of the cosmos shifts. Dark matter has structure. Extraterrestrial civilizations exist. The galaxy is stranger and more dangerous than we thought. And we, as a species, have to reckon with the fact that we're not alone, and that our models of reality are incomplete. Which direction we take depends on the data. And the data is coming. December 19th, the IWN monitoring campaign, the JUICE observations, gamma ray searches, all of it will converge over the next few months to give us a clearer picture. But data alone is not enough. Data has to be released. Data has to be analyzed. Data has to be communicated. And right now that process is not working as well as it should. The high-rise images taken over a month ago are still unreleased. NASA's response to questions about 3IATLAS has been curt and dismissive. The JPL Horizons data showing perfect and plane acceleration has been acknowledged by no one in an official capacity. There is a pattern here, a pattern of silence, and silence when dealing with something this significant is corrosive. I want to be clear. I am not accusing anyone of a cover-up. I don't think NASA is hiding evidence of alien technology in a vault somewhere. I do not think there is a conspiracy to suppress the truth. What I think is happening is more mundane and in some ways more troubling. Institutional inertia, risk aversion, a culture that punishes bold claims and rewards caution, a system where it is safer to say nothing than to say something that might be wrong. This is understandable from a career standpoint. Scientists build reputations on credibility. If you claim to see something extraordinary and you are wrong, your reputation suffers. Colleagues question your judgment. Funding agencies are less likely to support your proposals. Journals are less likely to accept your papers. The incentives push toward conservatism. Do not make waves. Do not stick your neck out. Do not be the person who claimed to find aliens and got laughed out of the field. But conservatism has a cost. It slows discovery. It prevents us from exploring the edges of possibility. It makes us miss things that are right in front of us because we are too afraid to look directly at them. And in the case of 3IATLAS, it is creating a vacuum where speculation and mistrust flourish. When official institutions are irresolute, people fill the gap with their own explanations. Fortune posts, Reddit threads, YouTube videos. Some of it is thoughtful and well-researched. Some of it is nonsense. But all of it exists because the people who should be explaining the experts with access to the best data are not talking. Or they're talking but only in dismissive two-sentence statements that do not engage with the substance of the questions. Avi Bay has been vocal about this. He has been pushing for transparency, pushing for the release of data, pushing for serious consideration of alternative hypotheses. And he has been criticized for it, not because his arguments are wrong, but because his willingness to entertain the possibility of artificial or exotic origins makes people uncomfortable. He's accused of seeking attention, of being unscientific, of damaging the credibility of astronomy as a field. But this criticism is backwards. Science is not about avoiding uncomfortable ideas. Science is about testing ideas, uncomfortable or not, and seeing which ones survive. Lowe is doing science. He is proposing hypothesis. Hayes making predictions. He is pointing to data that does not fit the standard model and saying this deserves explanation. That is exactly what ascientists should do. The people who are being unscientific are the ones who dismiss the anomalies without engaging with them. The ones who say it is just a comet without explaining the nickel-twiron ratio, or the thermal lockdown, or the perfect in-plane acceleration. Theones who delay data releases and Refusedo answer questions and act as if transparency is optional. If 3IATLAS is just a comet, prove it. Release the high-rise images. Show us the debris cloud in December. Measure the gamma ray flux and show that it is consistent with background. Do the work. Do the observations. And then present their results openly and honestly. If their results support the comet hypothesis, great. If they do not, acknowledge it and move on to better hypothesis. That is how science progresses. But what we're seeing instead is stalling. Silence and an unwillingness to confront the possibility that the data might be telling us something we do not want to hear. This matters because the window is closing. 3IATLAS is leaving. By the end of 2026, it will be too faint to observe with most telescopes. If we do not take advantage of the time we have, if we do not gather the data we need to settle the question, we will be left with uncertainty, a permanent what if, and that uncertainty will fester. Decades from now, people will still be arguing about whether 3IATLAS was natural or not, because we did not do the observations when we had the chance. So what should happen? What comes next? First, release the high-rise data now, not next month, not after peer review. Now. The images are publicly funded. They were taken by a mission paid for by taxpayers. The scientific community and the public have a right to see them. If they show a normal comet, fine. If they show something weird, even better. But the data needs to be public. Second, point a gamma-ray telescope at 3IATLAS. Fermi New Star, any instrument with the capability to detect a steady non-thermal flux in the range predicted by the Cub hypothesis. This does not require a massive investment. It requires a few hours of observing time. If the signal is there, it is the discovery of the century. If it is not, we rule out the Cub hypothesis and move on. Third, conduct a systematic search for subprobes. If 3IATLAS is artificial and release satellites, those satellites might still be in the solar system. They would be small, faint, hard to detect, but not impossible. Dedicated surveys of unusual orbits, radio monitoring for anomalous transmissions, infrared searches for objects with thermal signatures inconsistent with passive bodies. This is speculative, yes, but if the stakes are as high as they might be, it is worth doing. Fourth, prepare for December. Coordinate observations among multiple observatories. Make sure Hubble and Webb are scheduled to observe. Make sure ground-based telescopes with spectroscopic capabilities are ready. Make sure the data processing pipelines are in place so results can be analyzed quickly. This is a once-in-a-lifetime opportunity. Do not waste it. And fifth, be transparent. When the data comes in, share it quickly, openly with clear explanations of what it means and what it does not mean. If the debris cloud is there, say so. If it is not, say so. If the interpretation is ambiguous, explain why. Trust the public to handle complexity. Trust the scientific community to debate the implications. Do not sit on the data and hope the controversy goes away. It will not. Now let us talk about implications. If 3IATLAS turns out to be natural, what do we learn? We learn that comets can form with wildly unusual compositions. Well earned that nickel tetracarbonyl, a compound we thought was purely synthetic, can occur naturally under certain conditions. We learned that interstellar objects can have properties that challenge our models. This is valuable. It expands our understanding of planetary system formation. It tells us that the universe is more diverse than we thought, but it does not fundamentally change anything. We refine our models and move on. If 3IATLAS turns out to be a cub, what do we learn? We learned that dark matter is not an invisible particle. We learned that it has structure and mass and can interact with normal matter in observable ways. We learned that the galaxy is full of macroscopic dark matter objects, some of which pose an impact threat to Earth. We learned that cosmology needs to be revised. Galaxy formation models need to be revised. Particle physics needs to incorporate new fields and new symmetries. This is transformative. It is a paradigm shift. It is the kind of discovery that happens once a century if we are lucky. If 3IATLAS turns out to be artificial, what do we learn? We learn that we are not alone. We learn that other civilizations exist or at least existed, and that they have the capability to send probes across interstellar distances. We learn that the galaxy might be full of ancient artifacts, messengers from long-dead civilizations drifting silently through the void. We learn that the Fermi paradox has an answer, and the answer is not that we are unique. This is the most profound discovery humanity could make. It changes philosophy. It changes religion. It changes how we see ourselves and our place in the cosmos. Any of these outcomes is possible. The data has not ruled anything out yet. And that is what makes this moment so important. We are not looking at a comet that we understand. We are looking at something we do not understand. And the only way to understand it is to look closer, to gather more data, to test hypotheses rigorously, to be open to the possibility that the answer might surprise us. The next 6 weeks are critical. December 19th is the test, the moment when the debris cloud either appears or does not, the moment when we either confirm the comet hypothesis or have to start taking alternatives seriously. And beyond December the next year, the IBM campaign, the gamma-ray searches, the tracking of activity as the object moves into the outer solar system, all of it matters. All of it contributes to the final picture, but none of it happens if institutions do not do their job. If data is not released, if observations are not made, if transparency is not prioritized, the science is ready. The instruments are ready. The only thing missing is the will to use them properly. So here is my message to NASA, to ESA, to the research teams working on this. Do your job. Release the data. Make the observations. Be transparent and let the science speak for itself. If you are right and 3IATLAS is just a comet, the data will confirm it. If you are wrong and it is something else, the data will show that too. Either way, we need to know, and we need to know before it is too late. And here is my message to everyone else. Pay attention. This is not clickbait. This is not hype. This is a real scientific question with real implications. We have found an object that does not fit our models. It might be natural. It might be exotic. It might be artificial. We do not know yet, but we will know soon. And when we do, it will matter. December 19th, 45 days from now. The reckoning. The test. The moment when speculation either becomes confirmation or fades into noise. Watch for it. Ask questions. Demand transparency. And remember that science is not about having all the answers. Science is about asking the right questions and being brave enough to follow where the data leads, even if it leads somewhere we did not expect. 3IATLAS came from the darkness. It passed through our solar system. It did things we cannot fully explain. And now it is leaving, carrying with it the answers to questions we're only beginning to formulate. We have a brief window to understand it. A few months, maybe a year, and then it is gone forever. Do not let the window close without looking. Do not let institutional caution or fear of controversy prevent us from seeing what is right in front of us. Do not let this be the moment we look back on decades from now and say we had a chance, and we missed it. Because if we miss it, if well at 3IATLAS disappear into the void without understanding what it was, we will never know. Was it a comet? Was it a cue ball? Was it a probe? The universe will not send us another one just because we were not ready the first time. This is it. This is our chance and we need to take it. So watch the data. Watch the December observations. Watch the gamma ray searches. Watch the ION campaign. And most importantly, watch the response from institutions. Are they being transparent? Are they releasing data? Are they taking the anomalies seriously? Or are they stonewalling, hoping the controversy dies down so they can go back to business as usual? If they stonewall, call them out. Demand better. Science is a public good. Data collected with public funds belongs to the public. Transparency is not optional. It is a responsibility. And when that responsibility is not met, people have a right to be angry. But if they step up, if they release the data and make the observations and engage honestly with the questions, then support them. Thank them. Recognize that doing science in public under scrutiny with high stakes is hard. And acknowledge that the scientific process, messy as it is, works eventually. The next few months will tell us a lot. Not just about 3IATLAS, about how science is done, about how institutions handle uncertainty and controversy, about whether we as a civilization are mature enough to confront the possibility that the universe is stranger than we thought. I hope we are. I hope December brings clarity. I hope the data, whatever it shows, is definitive enough to settle the debate. And I hope that when we look back on this moment, we can say we did it right. We asked hard questions. We gathered good data. We were transparent. And we learned something profound. Because that is what science is for. Not to confirm what we already believe, but to show us what we did not know. To surprise us, to humble us, and to expand our understanding of the cosmos and our place in it. 3IATLAS is leaving. The clock is ticking. And the universe is watching to see if we are paying attention.